Okay, it's audible. Thank you. Okay, so I'll start with some Blackboard stuff, a little bit of things that it's a few things about Fluke stuff that I wanted to talk about. So in the last lecture, what I have shown is that because of some dynamically disconnected sectors that may emerge in the Hilbert space of a many-body system, one can have violation of ETH, and we have discussed at least one example of that where the violation is quote-unquote weak, meaning that it holds for a special set of states, and these states are often called quantum scars. Today, the plan is to do two things, which I'm surely not going to be able to achieve. But the first thing is to show you that these things also occur for periodically driven systems, not just for Hamiltonians in equilibrium. And for that, I would need the Fluke formulation, which I'm going to very sketchily discuss on the Blackboard for 2 minutes. And then we are going to show what happens when you drive a system which has inherent scars, how the Fluke Hamiltonian of that system behaves. After this, I'm going to go into the other topic, which is Hilbert space fragmentation, and not really say much about it, except that, I'm going to kind of give you a heuristic picture based on some simple models. And then, if time permits, we're going to show that even this Hilbert space fragmentation can be realized in Fluke systems, but that probably I'm not going to be able to make it to, but let's see. Okay. So, let's start with this Fluke stuff. So, what is this? So, usually I always, whenever we have a quantum system, we always have a Schrodinger equation, which in principle can involve a Hamiltonian, which depends on time. Yeah, sure, please. Can I? Oops. Okay, is that fine? So, and here I'm going to sort of say that this Hamiltonian has a time dependence, so that it has a period, and this period is given by capital T, which is often 2 pi by omega d, which is the drive frequency. And I'm going to take the simple case where I have a single drive frequency in the system, and one term of this Hamiltonian is driven. Some parameter is changed periodically in time. Now, this equation can be converted into an equation for the evolution operator of the system, which is defined by psi of t. Okay. So, we know that in quantum mechanics, this evolution operator is what propagates the state. And if this Hamiltonian didn't have the time dependence, then this evolution operator can be formally written as e to the power minus IHT over h bar. Just that. Okay. Now, when you write this and you actually do the math, one thing that comes in this exponentiation, and this is not very well realized in quantum mechanics, well written in quantum mechanics textbook, is that Hamiltonians at different times commute with each other. If this doesn't happen, this exponential form doesn't work. So here you see we have a problem, because I'm varying these parameters of the Hamiltonian as a function of time, and therefore Hamiltonian at different times may not commute with each other. Okay. So how do we get around these problems? What we do is that we break this time evolution into discrete steps, delta t, okay, and so that within that delta t, the Hamiltonian is roughly constant, and I can kind of exponentiate this using this, this stuff. So then my total okay, so then my total this thing is u1, u2 all the way till un, where n is roughly, where this delta t is roughly t over n, and un basically takes it from utn to some tn minus 1, okay, where this separation is of the order delta t. And this, because the delta t is so small, I can certainly write this as exponential IH delta t, by h bar, and I have to evaluate this Hamiltonian at a time between Tn and Tn minus 1. But if delta t is small enough, and this small enough is a thing that depends on different parameters of the Hamiltonian, including the drive frequency, etc., then I can just evaluate it at any time in between. So let's take, Tn, or I could take the midpoint or some such stuff. Okay. The claim is that at ordered delta t, it really doesn't matter. So now, this thing is typically symbolically written as time ordered product of e to the power minus I h t prime dt prime 0 to t. Okay. So whenever you see this time ordering and a cumbersome expression like this is what it really means. Okay. This doesn't mean that you can do the integral within this and be done with it. Okay. And this is why time ordered stuff is so hard to evaluate. Okay. Because you have to do it in units of stuff. But say we can, so basically, I'm going to talk about this U, the evolution operator, for the rest of this stuff. And therefore, let me just sort of analyze it a little bit more in the context of periodically driven systems. Okay. Now, there is this other thing that many of you know, but if you haven't seen it, it's probably good to sort of take a look at it. And that goes by the name of Fluke theorem, which says that if you have a set of differential equations, let's say x of t, t is any parameter, not necessarily time, which is a of t x of t, where x is a column vector and a is a n by n matrix and stuff like that. And if a of t is periodic, okay, then the solution of this can be written in form of x lambda of t, which is this period, times a function which is periodic in time. Okay. This is this Fluke theorem. And you see, this is what gives you the Bloch theorem in condensed matter, because there this parameter is x and you have periodically broken translational symmetry, so that this thing becomes ikx, and this is a periodic function of x. And in here, because you have broken time translational symmetry in a periodic manner, what you can say is that my ut0 is a piece which depends on, and I'm putting this I because there is a factor I here on the right side of Schrodinger equation. Here there is none, but if you just change it, it's just going to give you this I. And then some pt of 0. This factor doesn't depend on time. It just depends on the time period. Okay. Typically, we write this as e to the power some Hamiltonian-like form t times t over h bar. And note that this I can always do, provided I am okay with keeping the period dependence within Fluke Hamiltonian. This is called the Fluke Hamiltonian of the system, and you can keep the time period within dependence of this Fluke Hamiltonian. And then, of course, this is just lambda t by t, right? So I can always write it in this form. Okay. And p is a function which is periodic in time. Okay. And here there are some arguments, but let me just give you one. So so for n cycles of the drive, unt0, this will just be, so you just replace this by, it turns out that you can write it in this form, nt and then p t0 again. Okay. The point is that in here, there are certain arguments which I don't want to get into the details of. They say that as long as you are willing to sacrifice a global phase dependence, which really doesn't matter, you can set this to identity, the P matrix. And one way to see this is that if you just think of this evolution operator at t equal to 0, this means that it has to be identity. And this can be done by putting n equal to 0 out here. So P00 has to be identity. And therefore, P capital T0 has to be identity because it's a periodic function. So as long as we are looking at stroboscopic measurement, that is, I only measure the system at t equal to 0, t equal to capital T, t equal to 2 capital T, and so on, then I'm perfectly okay with writing, I'm perfectly okay with computing this quantity. Okay. This, of course, doesn't hold if your time is not an integer multiple of capital T, because then you have to really think of this p t0 function. This part of this thing gives you what is technically called a micromotion, that is time evolution between two periods, and this tells you about the stroboscopic time evolution. So in whatever I'm going to do, I'm going to just look into this stroboscopic time evolution and therefore deal with this Fluke Hamiltonian, okay, this HF of NT. And since knowing HF of T, quote unquote, means that I know my ut of 0, I still have to exponentiate it and stuff like that, but at least symbolically I know this. So people have been trying to sort of calculate this HF of T in several systems. Unfortunately, it's not that easy. The reason is that ut0 is also this time ordered exponential t to 0 I by h of t prime dt prime, okay, and this is equal to e to the power minus I hf of t h bar, okay. Because I have already told you that ut0 is given by this, and then these two must be equal. And using this, I can have a relation of hf of capital T in terms of hf of h of t prime. It's integral actually. But you see that this is a horribly complicated stuff to calculate because of this time ordering, okay. And also otherwise because exponential of operators, and yeah. So these are not too easy to think. So people have developed several approximation schemes for doing this. One of them is the high frequency expansion, which is, yeah. No, for the original, so time independent Hamiltonian, the Fluke Hamiltonian and the Hamiltonian is the same thing. I mean, it's just the, you just say HF is H and that's it. Yeah. Sorry, there is a minus sign here somewhere in my convention, but okay. Yeah.
So, with the arguments, why you are writing this lambda as just linear means it's linear?
No. So this is lambda of T. So I can always write it in this form, and the reason I am writing is that typically, when we talk about evolution, we are accustomed to seeing some Hamiltonian-like stuff, T divided by h bar, etc. So it's just to cast it in that form. Difficult because no, you can in principle, but actually the problem is I'm not sure that you can regulate it because once probably, I mean, provided that this quantity is positive definite, then maybe yeah, but I haven't really thought about that in that. But in principle, it's possible. At least in the CFT context, I know, and there is at least some concrete calculation that people have done this. For the generic Hamiltonian, I need to check. For a many body stuff, I don't really know.
I could just make a comment.
Yeah.
So there are a couple of works actually written more by Anders Sandberg and Anatol who were talking about,
Yeah.
where they did what you're saying in certain specific contexts and maybe you could look at this.
No, those things, there is this one problem also that continuing it for large times is incredibly difficult.
They just did it for a few.
See, there is a mathematical question here. So let me just tell you that. So this is an oscillatory function in time, right? So suppose I calculate a correlation function after n cycles of the drive, okay? I'm going to get some finite answer because it's an oscillatory function, right? Now think of doing the same calculation with imaginary time. If this n cycles is large enough or this time is large enough, you get something which is very close to 0. Now, how do you analytically continue unless you know the exact analytic continuation to get a finite number from 0? I mean, that's not an easy thing by any stretch of imagination, right? So, okay, let me just continue with this. Oh gosh, I'm already behind time. So one approximation scheme that one does is this, what is called this Magnus expansion, which means high frequency expansion. So this is valid when the drive frequency is very high. Okay. See, you see that when the drive frequency is very high, this time period is close to 0. So whatever this integral is, its value is very small, and therefore I can, say that 1 minus I HF, and this is a very crude way of doing this, I really apologize, is 1 minus E to 1 minus I by h bar 0 to t integral ht prime dt prime, okay, which tells you that your HF is just your average of h over the time cycle, because this integral divided by t, capital T, is just the average. Okay. So this is the first order, and this makes sense because if you drive a system really, really fast, what happens is that over a certain time scale, the system just sees the average. Okay. And then there are corrections to this, and these corrections typically come as commutators of Hamiltonians at different times. So for example, if you calculate HF2, and I really don't know if I'm making a mistake out here, but it's something like dt1, 0 to t1 dt2, ht1, ht2, commutator, okay, something like this, and so on. Okay, there are all these nested commutators that keep on coming. So this is one, but I'm not going to deal with this particular way of calculating the Fluke Hamiltonian. What I'm going to work on is something else, which is called Fluke perturbation stuff. So what it means is that I'm going to consider a situation where the Hamiltonian has two terms. One is H0 and the other one is H1. This H0 is a function of time, and this H0 is essentially some lambda t times some operator O, and the amplitude of this lambda t is really, really large compared to all other scales in the problem. So it's a large drive approximation rather than a large frequency approximation. Okay. So if this happens, then to 0th order, I can ignore my H0 as H1, and I can say that since this operator is going to, at different times, are going to commute with itself, and this is the only operator in the problem, I can always write my U0 to be e to the power minus I-O t over h bar times integral of lambda t prime dt prime 0 to t. I can do this exponentiation because now the problem of having Hamiltonian not commuting with itself at different times is gone. So this is almost like this. You can do this differential equation calculation and just you will get this. And then for H1, the other terms, and so let's say that this is e to the power minus I h bar t O, and then let me call this as some alpha of t. Okay, I can do this integral and whatever the result is, it's some alpha of t. I'm also going to take alpha of capital T to be 0, choose a function such that this happens. For example, if you choose this to be cos omega d times t, then this is going to work. So that's an example. Okay. In this case, HF0, which is U0 of T0, is just 0, because U0 of T0 is identity and HF0 is therefore 0. Okay. So I'm going to work in 4 cases where this is true. And the only thing that I want to show you, which is the other part, is that now how do we tackle for this H1? So what we do is that we go to eigenbasis of H0, and let's say these are n and epsilon n. These are eigenbasis of the operator O. Okay. And what I do is that I just do a perturbation theory that you see in your standard quantum mech book. Okay. So H1 is just minus I by H, sorry, U1, the first correction to the evolution operator is 0 to t dt U0 dagger H1 U0. Okay. And I can evaluate this. Why? Because now I can compute the matrix element Mn where these are these bases. Okay. And you see that this will just give me some phase factors that will come in. because you see that this quantity is some alpha t times this part, but that operator acting on m and n is just going to give me some epsilon m and epsilon n and stuff like that. So what I'm going to do is just have an integral e to the power minus I alpha t okay, so there is a t, fine, I can put that, no problem, epsilon m minus epsilon n by h bar. And then this quantity is just m h1n, a matrix element of h1 between these two steps. Okay. And if you evaluate this you can easily evaluate if you know the function alpha of t. And once you do this, you get the generic answer is that you get an f of t, which is because of this integral, times h1, and which depends on m and n because of this epsilon m and n, times some h1 mn, okay, summation over m and n. And therefore my u1 is of course summation over m and n, f mn, h1 mn, m n. So that's the representation of u1 in the eigenbasis of h0. Okay. And knowing this, I can find out how the Fluke-Hamiltonian looks, because I have to divide it by some factor of capital T and stuff like that. Okay, those factors. Part of Hamilton, I'm taking in this to be independent of time. If not, your integral is going to be a little bit more complicated. That's all. But in most cases, I'm going to use this. Okay. So the point is that this gives me a U1. Okay, and then there are higher powers, but those are typically suppressed when you are either in the large frequency limit or large amplitude limit. So this U1 controls the dynamics of the system up to a large time scale, after which other terms in the Fluke-Hamiltonian will kick in and lead it to thermalization. But what I'm trying to say is that you see that if this is, okay, sorry. Okay, thanks, sir. So if you now have this U0, which is this U1 plus U2 plus etc., this thing gives you an order, let's say 1 over omega d suppression, which means that these terms are going to come in only when you have driven for a large number of cycles, their effect, and further this thing. So if this suppression is large, there is a long time. Use black pen, okay. Otherwise, this recording is a problem, or? Okay. So this means that there is a suppression, and therefore there is a long time scale up to which the physics is dominated by this U1. Okay, and that's a typical pre-thermal time scale, which we are going to see. So now, yeah.
This particular one can use in smooth.
In what?
In smooth, non-periodic.
Non-periodic, but the thing is not going to be that simple because.
So only alpha t is 0.
Yeah. So here you see the alpha t is alpha t is probably identity there. I mean that's sure. But there is no analog of capital T. So you will have some operator times T, and then is the standard perturbation theory, right? Standard time dependent perturbation theory. Here, okay. So this is also called standard perturbation theory, but in the rotated basis. So you have gone into the Fluke basis, and then you are doing your perturbation theory. So that's another way of looking at it. But let me now stop this formulation. So this is all that I wanted to say. I'm going to use this formulation somewhere and give you examples where this is. So let me go into this this stuff. So before doing this, let me take this opportunity to thank all my collaborators. And 3 of them are at least in this room. And I must tell you that if you have any questions, go to them, not to me. Because they know all about all the works that has been done here. And I would also like to take this opportunity of doing something that I should have done at the beginning of the talk, that is thank the organizers for inviting me and or arranging this meeting. Okay, and if you are interested in the details of this, there are a few works out here. Okay, so I need to use this. So Okay, the first thing that I want to do is that yesterday I told you about a model called the Rydberg model, and I want to motivate that model a little bit from experimental stuff. So what happens is that there are these ultra cold atoms, which are system of rubidium atoms. The ground state of these atoms are given by this G, okay, and the quantum numbers are given out here. And the excited states, there is a excited state R to which you can excite these Rydberg atoms, and that's called, that's this state, okay? It's a really high state. The point is that if you put the correct, combination of lasers and stuff like that, you can develop a two-state model at every site where the Rydberg atoms flips between the ground and the excited state, okay? So there are technical ways of doing this, and there is a very nice paper by the Harvard group, Marcus Greiner and others, which explains all the details of this, okay? But without getting into the details, what can happen is that when you excite an atom to a Rydberg state, you pay an on-site energy cost, which is the difference between the sum of the frequency of these two lasers that you put in and the difference of the energy level out here. So this quantity delta is typically called detuning, which tells you that how much the frequency of the two lasers, the red and the blue out here, is different from the energy spacing of the levels. When they are exactly same, you are at resonance, but you don't really want to, well, you can go there, no problem, this thing, but you can tune this. Okay. There is also this other thing that because you are putting in this laser, and there is an intermediate state using which you can sort of get into, so you can first get into this excited state and then to this other state. And that process is a second order process which has the following, this thing, where this small delta is the detuning of the blue laser with respect to this ground and this E state, okay? So this tells you the amplitude of effective coupling between the ground and the excited state, okay? So this is a 2-photon process. So first you have to absorb a blue photon and then to a red photon to go there. And while coming back, you do the same. Okay. And the point is that these Rydberg states, it's well known that if you put an atom in that Rydberg state, it experiences a strong van der Waals interaction with any other atom in the system which is also in the Rydberg state, but not if the other atom is in the ground state. It's only an interaction between two atoms if they are in their Rydberg excited state. There is some atomic physics reasons for this. I'm not going to get into the details of it. And therefore, there is a term like this, okay? It tells you that if you have two Rydberg excitation, where this Ni gives you the number of Rydberg excitation on a given site, which could be 1 or 0, then you have an interaction potential. And if this potential is strong enough, you get the Rydberg blockade, which I talked to you. So what are the phases of this? But even before that, how do you measure, okay, in an experiment? So what you do is that you prepare the state with this 2D or 87 Rydberg BEC, okay, of some atoms, and then you put it on a square optical lattice. Okay, there is technically it's called projecting a lattice onto these atoms, which one can do by some clever application of laser. They just put standing wave of laser, which creates a lattice. But after the state is prepared, and then you let the system equilibrate and you prepare the state. But after the state is prepared, the first thing you do is that you ramp up this laser intensity. Okay? So the lattice becomes very, very deep, which essentially means that your tunneling process is exponentially suppressed. So the atoms really cannot move from one lattice site to the next, because that's an exponential process when in the lattice depth. So your tunneling time is very large. So you apply, and then you apply a light which is tuned, and only the experimentalists know how to tune this, not me, such that if you have 2 or any even number of atoms within a given lattice site, they just scatter off each other using this light and go out of the trap. Okay? So it's a light-assisted collision process which ejects pair of particles from the trap. This means that if you have even number of particles in a given, within a given lattice site, then at the end of this collision process, you are most likely to see 0 number of bosons or these atoms inside the trap. But if you have an odd number, then 1 will be left, because that doesn't have a pair and it cannot get scattered. So this process allows you to detect the parity of occupation of the atoms inside the trap.
And when you are saying one, that is in the excited.
That is in the excited state, yeah. So whenever I say atom now, it will be in the, and therefore this is what happens, you know. What this, yeah. So and therefore, if your detuning is large, so let's come back to this Hamiltonian. So if your detuning is large, okay, you are going to create as many Rydberg excitation as possible, okay. However, you cannot create them arbitrarily because that would be too much of a cost of this Vij. So if in the limit that you are prohibiting 2 consecutive Rydberg excitations, then the most you can do is to create one, then give a gap, create the next, give a gap, and this leads to a Z2 ordered state because it's a typical antiferromagnet, you know, in the spin language. Up is like occupation, down is like no occupation. But you can go to others. So if you increase your lattice strength, you can have Z3 ordered and Z4 ordered because you are making this more and more difficult, you know, as of having 2 Rydberg excitations nearby as you increase your potential. So now what they did is the following. They prepared this thing in this Z2 ordered state, and then they quenched the Hamiltonian, okay, such that delta is tuned to 0. Okay, but if delta is tuned to 0 and you have this, you know, constraint of having no 2 excitations on neighboring sides, then this model, okay, is exactly the PXP model that I wrote down in the last lecture. Okay, and so your dynamics occurs via the PXP model, and your starting state is an antiferromagnetic state, and that's exactly how they do this in experiment. And once you do this, you see this long time oscillations, which is ETH violating. Because this microsecond is a really large time scale when it comes to this kind of systems. And order 1 time scales would be, you know, I guess a fraction of a microsecond or something like that. I don't have the number at the top of my head. Close to 0.1 or 0.2 microseconds. But you keep on seeing these oscillations. And you also see the amplitude of these oscillations die out after this some value, which means that your scar space was not really exact, the thing that I was trying to say. So, yeah.
Probably also means that the system is talking to the environment.
No, these are very well isolated systems actually. Yeah, I think so, because the reason is that, you know, this coherent, so if the system was talking to this environment, it must be talking through some processes whose time scale is really large. And yes, there are processes like that, but those are typically in order of milliseconds. Yeah, because that's how long you can keep this kind of system stable by maintaining coherence. That will also lead to destruction of coherence, and it's not happening within this time scale. I mean, that's my understanding of it. I need to revise my numbers, but that's the last time, yeah. So this can, of course, also happen if the system is talking to the environment, but in this particular case, I don't think that's the case. Okay, I'm going to skip all this. Maybe just this stuff. So this again is that if you have a Hamiltonian like this, and you have a case where V0 is large enough, you can write it in this form, okay, where this projection is there. Okay, so you can write it in this sigma x tilde form, and that's something that we are going to look into. Okay, so now I'm going to talk about what happens when you have these quantum scars. But instead of looking in this model, now we are going to drive this periodically as a function of time. So what do we drive? We drive this quantity, this detuning parameter of the model as a function of time, and we are always going to restrict ourselves in a regime where V0, which is the nearest neighbor coupling between 2 Rydberg excitation, is very large compared to all other systems. So we are effectively in the Hilbert space where the states are the only states that are allowed that doesn't have this V0 energy cost. Okay, so no 2 up spins on neighboring sites. That's pretty much the case.
And you're starting from the same Z, that Z2.
Yeah, I'll start from Z2, and given the time, I'll only probably start from Z2. So although there are more slides here, but yeah. So what do? We calculate the unitary evolution operator. This is numerically done. So we use a square pulse protocol where lambda t becomes plus lambda and minus lambda at 2 half cycles. It's a square pulse. In the first half, it's plus lambda, and the second half, it's minus lambda. And what do? We basically compute the evolution operator like this. Okay, it's now a product of two thing, one for the first half of the cycle and the other for the second half. And to numerically exactly calculate this, we diagonalize h of lambda and h of minus lambda, go to these bases and then just stitch them up. Okay, so this is done by Bhaskar and with all this numerical diagonalization stuff. So what do we study? We study the evolution of the density correlation function, NL and NL plus 2, that is correlation between neighboring sites. And we take not L plus 1 but L plus 2 because it's an antiferromagnetically ordered systems, and it makes sense to do this. And then what we want to calculate is just this. Okay. So the knowing the eigenvalues and eigenfunctions, I have expression for this in terms of that, and so numerically I can explicitly calculate this. But then we also want to calculate the Fluke Hamiltonian of this analytically and using a large drive amplitude approximation, which means that this parameter lambda, which is the amplitude of the drive, because I'm going from plus lambda to minus lambda, so the amplitude of the drive is proportional to lambda. That is a large quantity. If that is the case, then this term is my U naught, okay, and this is my operator O that I wrote down, okay, and I know what U naught T is, okay. This is a simple calculation, and one can do this, and then I can do my first order perturbation, just like what I have showed. It's a few lines of calculation, but you can try to look at it. Interesting point is that for this kind of drive protocol, this function Fmn that I have talked about turns out to be a function which is sine gamma by gamma, where gamma is lambda t over 4. What does this mean? That at special frequencies where lambda t by 4 is integer multiples of pi, this HF1 vanishes, okay, and therefore all the dynamics essentially is controlled by HF2 or higher orders, and those are much more complicated Fluke Hamiltonian. In fact, it turns out that for this drive protocol, HF2 vanishes and HF3 is the next leading term, okay, and that essentially is much more complicated. But what is the difference? The difference is that look at this form of HF1. This is exactly like a PXP model. This is like a rotated PXP model because it has this sigma x tilde and sigma y tilde, which is just a rotated version of the standard PXP. So you would expect that this model will also host quantum scars in its eigenspectrum, just as the original PXP model did. However, if this term goes to 0 and the Fluke Hamiltonian is given by higher order terms, those are incredibly complicated 3-spin or 5-spin or 7-spin objects, which has no reason to host scars in their Hamiltonian. So at this special frequency, we are going to move away from a scar-induced oscillatory dynamics to a ETH-like thermal dynamics, and that's the thing that we showed. So this Fluke thing, what it does is that it allows a control parameter in the form of a drive frequency, which allows you to tune between ETH violating and ETH conserving dynamics. Okay. So this is an example. So let me just show this. So I'm not going to get into the details of this. So you see that there are, for very high frequency, the first order Fluke Hamiltonian is just the standard Hamiltonian, okay, because it's just the average Hamiltonian. So delta goes out of the problem because you average it to 0. So it's the PXP model, and you see the standard oscillatory behavior. This black line essentially is the ETH expected result obtained from something called the diagonal ensemble. And this red line is if you don't start from a Z2 state, if you start from, let's say, a all spin down state, which is something we call the vacuum state, and you see that there is no oscillation. So this gives you an example of why we call it a weak violation of ETH, because it depends on the initial state of the problem. But what happens if you go to very low frequency? Well, if you go to very low frequency, the Fluke Hamiltonian is an incredibly complicated beast. There is no perturbation theory, and all you expect is heating up to infinite temperature, because you are driving the system would very efficiently absorb energy, and it's going to soon go to an infinite temperature ensemble. And ETH is super good in that regime. Okay? So it just all matters. In between, something interesting happens. You see, you would expect typically that, you know, I'm in the high frequency, I see scar-induced oscillation. I'm in the low frequency, I see, you know, complete ETH. Maybe there is some typical frequency beyond which this ETH sets in, but that's not the case. Because here is a low frequency where you see these oscillations, and here there is a relatively high frequency where you see ETH. Okay? So it turns out that this transfer from high frequency scar-induced dynamics to low frequency ETH type of this thing, like dynamics, is non-monotonic. Okay, at least there are multiple entrances and re-entrances, and that is due to that sine function. Because you see, a sine function is periodic in drive, and so at special frequencies, this thing is going to be ETH-like, and this is something that we see. You see that if I'm at a frequency, okay, so let me just say that this 7.75 is roughly what the sine function predicts, or something close to it. Okay, so if I am at higher frequency out here, I see ETH-induced oscillation because my HF1 is still large, and you know I have this scar-induced oscillations out here. So as I come close to this special frequency, I see that these oscillations decrease and then they approach the ETH value very fast. Here, it's all ETH. That's exactly at the special frequency where HF1, or renormalized HF1, I should say, goes to 0. But you lower the frequency, you see that the oscillations return. Okay? This essentially means that it's a non-monotonic phenomenon. And what we found is a phase diagram like this, that when you decrease your frequency, you first hit the first 0 of the sine, and that's where this is ergodic. Then you hit the second 0, then you hit the third 0, and so on. And as you go to lower frequency, these regions sort of become more and more dense, and they encompass the whole phase diagram. So this is how you move from an ETH-like behavior at low frequency to a completely, ETH violating behavior at high frequency. And therefore, I call this frequency a tuning norm, which can go from one type of behavior to the other. So this is how ETH violation, this is an example, not this is how. This is an example of how ETH violation can take place in periodically driven systems through quantum scars. Okay. So, okay, I'm going to switch gear and start talking about thermalization, although 15 minutes. Vitarko, some bargain. I mean, you know.
Sir,
yeah.
this previous slide, you made by coherent thermal means which are...
Thermal means ETH obeying, coherent means coherent oscillations. Okay, yeah. Okay, I'm going to skip all this. Okay. Okay, so let me come to now the second example, which is called the strong Hilbert space fragmentation, where your Hilbert space fragments out to exponentially large number of fragments. Okay. Now, a few features that we already discussed in the last class, but let me go through this.
So, in terms of the original ETH criteria, that in terms of the matrix elements of the original Hamiltonian of diagonal matrix elements, is there some statement in terms of the Fluke?
No, so see, the point is that, okay, so let me, at high frequency, Fluke Hamiltonian is like a local Hamiltonian, okay, of some sort. So there you can again do this. But the problem is that none of these statements, etc., holds very well for long-range Hamiltonians, which are not local. And at low frequency, that's exactly what happens. In between, it depends on the ETH type of statement always holds. As long as you can write down a local Hamiltonian, and there is a radius of convergence for this perturbation theory, depending on the perturbation that you do. Beyond that, what happens when this perturbation fails, I really don't know. I don't know if there is a ETH-like statement. I don't expect one to hold. So, okay. so this Hilbert space fragmentation, so what happens is because of some dynamical constraint, the Hilbert space fragments into an exponentially large number of sectors. So if you are in one of the sectors, the Hamiltonian dynamics is not going to take you out of the sector. Okay. And this is something that one should note. The fragmentation usually happens in the computational basis, which is typically chosen as the fog basis in real space. So these are your site indices and this thing. I mean, this has to be the case because if you are in the eigen basis, everything is super fragmented because each eigenstate doesn't evolve, okay? So that's not the meaning of the fragmentation, it has to be in the computational basis. So, one very important point to note is that this is very different from separation into dynamically disconnected sectors which occurs because of global symmetries. Because those typically leads to number of sectors which scales algebraically with L. Here, the scaling is exponential. Okay. So it's not because of global symmetry. That's one important point that one would like to. So typically, what you do when you deal with this kind of system, you just resort to one symmetry sector, and you see within that symmetry sector, and you have to resolve all symmetries, and hopefully you can do that in a simple enough model. Within a given symmetry sector, whether you see this fragmentation, a dynamically disconnected fragment, and I'm going to give you an example out here. So, okay, so if the Hilbert space fragmentation is strong, then this is exponential. The number n being the total Hilbert space dimension and small n being the largest fragment, that ratio goes as exponential of minus L, which in turn means that there are exponentially large number of sectors. Okay. And quantum scars, the thing that I discussed, constitute a weak Hilbert space fragmentation where n by n tends to 1 in the thermodynamic limit because the scarce subspace is small and the rest is a huge subspace, and in the thermodynamic limit that just tends to 1. Okay, most of the models exhibiting strong HSF are 1D models, but there are some examples of 2D models. And Onnesha and Ornov are global experts in this, so you should ask them what these 2D models are. Okay. But let me come to the signatures of this HSF and Hilbert space fragmentation, which is something that I really want to spend some time on. The first thing is that, imagine that you have so many fragments. Ignore whatever this is, this belongs to a model which I'm not going to probably discuss because of time, but these are, fragments, okay? Suppose you are in one of these small fragments, what it means is that your evolution is going to probably show some signature of coherence because it's just a few states that is mixing with each other. However, you can be in one of the larger fragments, and there is exponentially large number of states. You are of course going to, there also you are going to of course see a signature of ETH because anyway it's exponentially large, but the dimension corresponding to that is going to be the dimension of this sector, not the full Hilbert space dimension. These subspaces, for mathematical reasons, are often called Krylov subspaces, for those who are interested in mathematics out here. And this, therefore, is called Krylov restricted ETH. It just means that you are accessing the Hilbert space of the fragment or this Krylov subspace of the entire matrix. Okay. One signature of this strong HSF is that the system retains memory of its, yeah.
Of course, trade-off restricted ETH is again the usual thing which you expect if you have a big trade-off subspace, but perhaps it's important to point out that there are again exceptions known where you have these big fragments, but they actually don't go to trade-off.
Yeah, that can also happen. That's actually true. Yeah, there are examples of that also. Yeah, sure. Yeah, so in most cases, this Krylov restricted ETH happens, and there are some cases where it doesn't.
Just like in most cases, polarization also.
Yeah, exactly. So, yeah. So, let's just come to this, this point. So, if you calculate an autocorrelation function, what ETH tells you is that by the time you have gone into this, the steady state, for a large enough system, its overlap with the initial state is minuscule. And in the thermodynamic limit, this should go to 0. For finite size system, it goes very close to 0. Okay. However, in this kind of systems, you can start with states and this autocorrelation is not going to go to 0. It's going to go to a finite limit. And there is a, so this statement is not entirely obvious because you can say, oh, I can choose a state which is in a very large subspace and it's not going to. But there is a direct proof of this. I'm not going to get into these details. There is a bound of this value. It's called the Mazur bound, but that's for, you guys can look at it whenever you want. The deviation of the entanglement entropy is another signature. What happens, and particularly think of a thermal system, if you take a typical state, okay. So, okay, let's just say that suppose you just take a typical state, then its entropy is typically given by its page value. Which means that this is the typical entropy of a thermal state that you pick up in your, and that goes as log of Hilbert space dimension, which is what gives you the volume law. Okay. However, here, okay, I really don't have time to get into this, but think of a typical value of the entanglement entropy, a value of the entanglement entropy for a typical state that you draw out of your Hilbert space. Typically, this state has volume law, which means Page showed that this goes as log of Hilbert space dimension plus some constant. So, but just think of this as a volume law where this volume is given by the Hilbert space dimension of this. The point is that when you go to this entanglement entropy, in this kind of fragmented system, you are going to get the symmetry resolved page value in the sense that, what I mean is that if you are in this block, for example, the maximum value you can get depends on log of the Hilbert space dimension of this block, plus some constant, etc. So, this would be different from your total entanglement entropy. And so these two essentially are markers which tells you that you have Hilbert space fragmentation. Okay. No. This figure is just a sketch. I have just drawn some few fragments and stuff like that. So, so let me not, okay. So I'm going to skip all this actually. Yeah. So let me now talk about a model, okay, which is a typical model. So this is a model of fermion hopping, okay. The point here is that the fermions can hop if and only if this operator, which is like a projection operator, is its value is 1, which in turn means that the fermion can hop only if the occupation to two sides to the right and one side to the left are equal. Okay. Let's just take this model at the face value. This is also a model of interacting fermions in the limit of large nearest neighbor interaction. You can do an effective theory which gives you this model, but let's not think about that. So what are the conserved quantities out here? Okay. The conserved quantity is the fermion charge n, that is the fermion number, total number, because I'm working in a fixed number. And also the number of bonds between two occupied sides is conserved. Okay. What I mean is that this can be split into sectors where you have n bonds, n plus 1 bonds, n plus 2 bonds, and so on. So the dynamics, because of this constraint, doesn't change the number of such bonds. Okay. So in fact, that is the constraint which is encoded in this projection operator. So a fermion can hop, but in this hopping, if it lands up in a site where there is a fermion to its right, then that hopping is constraint. So that essentially is this constraint model. So the largest sector of this corresponds to when n, the number, is L by 2, that is half filling, and the number of bonds where there are this nearest neighbor, so there are two simultaneous occupation and there is a bond between them, that's L by 4. So if I have a site with, so if I have a system with L equal to 8, then there would be 4 fermions and it would be arranged in such that there are two pairs. So this is an example, you see. So there is one bond here and another bond here, and this is an example of a L equal to 8 largest sector. So you will see that this state is completely frozen. The reason is that, think of this stuff out here. Let's say, I can take any one of these. So let's take this thing. So two sides to the right out here, I have empty side, and one side to the left, I have occupied side, which means that this projection operator is 0. So the Hamiltonian just obliterates this state, which means that it's a completely frozen state, which essentially again means that this, if you start with this Fock state, you are not going to evolve, okay? But there are other dynamical states. So for example, if you take a state like this where there are 3 particles giving you 2 bonds and another particle which is separated, this particle can keep on moving because 2 sides to its right and 1 side to its left, nx are the same. And these particles are particles like this in an otherwise frozen background are typically called movers. Let's not, I'll put it on a ring, but here, yeah. No, you can put it on a ring, there is no problem.
I was just wondering about these pictures. Is it open or on a ring?
This is open. This is open for me. Okay. But I'm going to soon put it on a ring, but yeah. So, and you see that these things, yeah, sure, I'll finish. So, so it can go from this, but this is also a fragment. It is not connected to this state by any means. Okay. So, and now let me show you why some counting argument for this fragmentation. The first thing is that I need to find out the number of states in the largest sector. Okay. So, to do that, we need to fill out L sites with L by 2 particles and L by 4 bonds. Okay, that's the largest sector of the theory. So here is an example for L by 8. So what do? I first put in L by 2 particles out here. Okay, so create 4 bonds on a ring. Now, but in doing this, if I don't put anything else, I also create several L by 2 bonds. Okay, and that's not the sector I want to be in. So how do I destroy these bonds? I just put in particles. Okay, so I now insert L by 4 empty sites so as to break L by 4 of this L by 2 bonds like this. And this can of course be done in L by 2 C L by 4 ways. Okay. So I have L by 2 links and I have to put L by 4 particles. The next, which is the most difficult part of this counting, which I am not going to explain, is that now you need to put L by 4 more empty sites so as to make it a complete ring without breaking any bonds. Okay? And it turns out that if you do a counting, this can be done in L by 2 minus 1 C L by 4 ways. Okay? This is a computation which can, well, there are different ways of understanding it, but I tried to do this and there is a, well, I spent significant time on it. It's very difficult to explain on a blackboard, so I'm not going to try. And therefore, you have this many L by 2 minus 1 C L by 4 times L by 2 C L by 4 number of states. But then there is also this inversion symmetry. You can replace holes by particles and particles by holes, and so there is a factor of 2. And this gives you a 2 to the power L number of states, okay? Divided by L, of course, but that's a subleading state. So this is the number of states. So how many sectors are there in this? So since I am explaining fragmentation, to do this, there is a very interesting counting argument. What happens is that you consider bounds on the number of fragments, okay? That can happen. To do this, you take, let's say, a site with 24, and you organize them in gaps of 8, okay? And you start with a frozen state like this, okay? Now, I'm going to create states, just count the number of states with one defect, okay? At most one defect per sector of this L thing. So what can I do? I can put a defect A, which means I can move one of these to the left like this, and this becomes mobile. I can or put a defect B, which means I can move this to the left and this becomes mobile. So if I have start with a configuration like this, I can generate 3 to the power L by 8 states because I can create a state. So for each of these L by 8 sectors, I can either leave it like that, or I can create a defect of type A, or I can create a defect of type B. Okay? So there are 3 possibilities in each L by 8 sectors. So the total number is 3 to the power L by 8. That's the number of states that I can create. Now, again, I don't want to get into the details of this. Now you can think of what happens when the Hamiltonian acts on this. And you can show that almost all of these L by 8 states can never be connected by the Hamiltonian. And the reason is that these defects can move, and you can organize in such a way that the left side of these defects are always the same, but the right 2 blocks will be completely different. And this is a thing that you cannot change by action of the Hamiltonian. It takes a little bit of thing on pen and paper to do, but one can convince oneself that that is the case. So up to a permutation of cyclic permutation, because I have put this on a ring now, you cannot connect it. But how many states can you connect by a cyclic permutation? That's order L on a ring of size L. So you have 3 to the power L by 8 by L such fragments, because these states cannot be connected by this thing. And this is a lower limit, okay? It's already exponential, but this is a lower limit because I have already connected, I've only considered 1 defect per sector. There could be more, okay, and that will give you more number. So this tells you that this constraint essentially just splits up your Hilbert space into exponentially large number of fragments. So, Deeptargo, can I take 3 or 4 more minutes, or should I stop? Okay, thanks. So this is an example of how in a constraint model Hilbert space fragmentation comes about. But now let me just give you one small example, and this is I'll just take 2 minutes. So I can play this Fluke game again with a model like this, where I take this Hamiltonian now with a nearest neighbor interaction, and I drive this interaction as a function of time. So I can either use a cosine drive or a square pulse protocol, and I play this game of calculating the first order Fluke Hamiltonian. So if you do this, it turns out a very interesting result comes in, that the first order Fluke Hamiltonian essentially have, okay, so this Aj out here is just this constant term, okay, nj plus 2, nj minus 1. So you see that if this f of t essentially goes to 0, okay, for some drive frequency, etc., then your first order Fluke Hamiltonian is exactly the constant Hamiltonian that I was talking about. Because it just has this 1 minus aj square, which means that you cannot hop unless you satisfy aj equal to 0. Okay. So, and this f of t is something you can compute within first order perturbation theory. What you get is a sine function for the square pulse protocol and a Bessel function for this cosine protocol, and each has its own zeros, and this gives you the special frequencies at which this phenomenon is going to take. But then there is this question that, look, this just happens in first order perturbation theory. You can go to second order, which we did for the cosine protocol, and there is no fragmentation like this. So everything is connected. The question is, in the dynamics, is there a large enough prethermal timescale where you can see this? The answer turns out to be yes, and let me just show you from this. Just this slide, and then I'll end. You see that here what we calculate is the entanglement entropy of an initial state after n cycles of the drive. So I start from an arbitrary initial state in my fog basis, and then I drive it after n cycles of the drive, and then at the end of that drive, I just take that state, construct the density matrix, half chain entanglement, and then I calculate that. Okay. So this is Shomshubro's work out here, and so if I'm away from these special frequencies, if I'm away from the special frequencies out here, you see that, okay, so what I have done is that I have taken this entanglement entropy and I have normalized it by the page value, which is the typical thermal entropy that you expect for this driven state to go to. So you see, as a number of drive cycles, if I am away from this special frequency, this goes to 1, which means that, you know, everything is okay and good, ETH is fine, I go to my page value, I should be happy. But here, as I increase my drive amplitude, I see for a large number of drive cycles, this doesn't go to page value, SP, but it goes to a SPF. Now, what is this SPF? While drawing this state, for this numerics, we drew it from the largest fragment. And that largest fragment has a page value, which is roughly 0.8 times the page value of the entire Hilbert space. And it really goes there. Okay? So this tells you that for a long prethermal time scale, and which it turns out is exponentially long in drive frequencies, this thing goes to the fragmented value. So this is a prethermal signature of Hilbert space fragmentation. More interestingly, you can now keep drawing random states from different blocks, okay, different fragments. And you see that depending on the fragment from which you draw it from, it goes to a different value. And this is a telltale sign that you must have this fragmentation stuff, because otherwise the drive really doesn't give you this feature. Okay? So this is a signature of prethermal Hilbert space fragmentation. It just takes this physics of Hilbert space fragmentation and gives it a platform for seeing this in periodically driven systems. Okay, so I think I'm going to stop here. Sorry for taking extra time, and thank you for your attention. Yeah. Yeah, sure. It's log of the Hilbert space dimension, roughly speaking. No, but that's the whole point. If there are exponentially large number of fragments, the log is certainly going to be small compared to, so if SP is 1 in some units, this is going to be a fraction. So here for the largest thing it's 0.8, but it's not going to go close to 1, because otherwise you are not going to have exponentially large number of fragments.
One more thing, why you are considering this NJ and NJ plus 2 also?
Oh, that's because you see here there is a constraint, right? If you have up, which is like sigma z, which is like nj, let's say, then the next thing would be down. So nj plus 1, that correlation would be 0 because of the constraint. So you are putting this thing that you haven't put 2 up spin on neighboring sites. So you are blocking that correlation anyway. That's always 0. So the next nearest neighbor is the second one. Thank you.
Okay, thanks, Deeptarko. Yes, I should also follow Krishnada's cue and thank the organizers for the very nice opportunity and organizing this very nice workshop. It's nice to have interact with the students, get your questions, and so on. So I will continue from where I stopped last time, and just to motivate how the talk will go. So the aim of this bunch of 2 lectures was the following: that yesterday I would have told you a bit about what these gauge theories are in a very pedagogical way, so that you are able to follow some literature that is currently being written, in the community. So that's what's going to be the theme for today, where we'll discuss various scenarios. But yesterday we didn't. I got some questions, and thanks for that. So I'll briefly go over some of the points just to make sure we are all on the same page, and then I'll go and talk about the results, right? So remember last time we talked about the Z2 gauge theories in 1 plus 1 dimensions and in 2 plus Z2 gauge theories, U1 gauge theories, both in 1 plus 1 and in 2 plus 1 dimensions, right? We said that in one spatial dimension, you need fermions to make the theories more interesting, right? But in higher dimensions, in 2 dimensions, 3 dimensions, and so on, gauge theories by themselves are interesting and can give rise to non-trivial dynamics. So let's continue this notion of understanding why is this dynamics constrained and interesting, right? So this is the example of a U1 lattice gauge theory, which is also called a quantum link model. And I'm going to give you the references today in the talk, right? So there was also a request for that. So we said that the most basic building block of such an object is a plaquette on a square lattice, for example, which has 4 terms. On a triangular lattice, we'll have 3 terms. On a honeycomb lattice, we'll have 6 terms. And on the square lattice, I can arrange the things such that I have U1, U2, U3, U4, and this is the plaquette operator, right? So of course, it's not a surprise that a U plaquette dagger would simply be U1 dagger, U2 dagger, U3 and U4. And the Hamiltonian you're going to write down is simply just a sum of U plaquette and the U plaquette dagger, right? And just to understand, right, how these states were all coming, because we said we are going to work with a spin half system. So no, these are labels that belong on a lattice, right? You have labeled it, it's your choice. So this term has a U1 for the first link. This term has a U1 dagger for the first link. That's important, right? You cannot change the labels. Its label is your computational basis, right? You have to label some things, and once you do that, it's fixed. Okay. So in the language of the spins, U was a raising operator. So it's a raising, lowering, right? Whereas this one is just the opposite. So this is lowering, raising, and raising again. Okay. So then we argued that there were 16 states. There was no confusion with that, as far as I understand. But now the 2 non-trivial states that survive are because how these raising and the lowering operators act on these states, right? So if I have a plaquette, right, which looks like this. So what are these arrows? These arrows mean that before you do this computation, you have to have a computational basis again, right? This labels the links. But the basis you choose, for example, could be the spin Z basis, right? The Z basis, where the spins are either pointing up or down. And then in that basis, you know that the raising and the lowering operator just raises and lowers the spin. So if I have something like this, then I'm using this notation that an arrow which goes to the right is actually a spin up. An arrow which goes to the left is a spin down, right? For the horizontal links. For the vertical links, an arrow going up represents up, a spin up, and an arrow going down represents spin down, right? This is just the notation, just so that all of us, we are on the same page. So now, if I have a state like this, right, then what happens is that the first term cannot act on this, because this is already in the plus half polarized state, right? So you cannot raise it further for a spin half. So it's going to get annihilated by the first term. However, the second term can act non-trivially. So the second term can act on this U plaquette dagger, right? U plaquette dagger can act on this, and it can lower this link, lower the spin polarization here. S2 can also lower it. S3 can raise it because it's a minus half. S4 can also raise it. So you get a plaquette where these arrows are flipped, right? So if I were to think of this as a line of electric flux going around a plaquette, I would have said that, look, this is an anti-clockwise orientation of flux. This is a clockwise orientation of flux, right? So that is the nomenclature that we have. And now you should be able to work out that if I have some configuration which is not a round the clock flux, right? It could be something like this. Right? So in such a case, both these terms should annihilate these states, right? Why? Because clearly the first term cannot act here because it's pointing up, so it's going to get annihilated. The second term, remember S4 has a dagger, so S4 cannot act here, so it's going to get annihilated. So out of the 16 possible states, we said 14, only 2 are of this type, right? So one has a clockwise flux, one has an anti-clockwise flux. The remaining 14 have various other orientations which the Hamiltonian is going to annihilate. That's the I think there was a question, and I hope this answers the question, right? Now another small comment is that so this was for spin half, right? Yeah. Sorry, what? They don't commute because remember these are the raising and the lowering operators. No, no. This is just an operator. I've just taken the dagger of it, right? That I can always do. No, yeah, so these different links commute. So link 1, link 2, so these are degrees of freedom, right? It's like saying phi. Yes. So yeah. So what does not commute is, so remember these U1, right? So a link has a spin S sitting on it. But a spin S is a 3-component object, right? So it has S plus, S minus and SZ. So it itself is a three operated object, right? So what we have identified is that S plus is U, S minus is U dagger, and SZ is electric flux. These don't commute with each other. That's the important point. Right. Okay, good. Now the second comment I want to make is that if you now take instead of spin half, right? If you take larger and larger spins, then I motivated that this goes to a quantum rotor, right? Because now all these values of spins are equally probable, and this goes to the quantum rotor. So in the extreme limit, where you have Wilson's lattice gauge theories, so you can identify this with the phase. And if I'm a bit fancy, I would write this as a something like this, where A mu is the vector potential that you conventionally learn in electrodynamics. Moreover, if you were to assume now that you are looking at very small lattice spacings, right? Remember, everything is on a lattice, and A is a lattice spacing. If you assume that A is very small, A is going to 0, then you can expand this, right? This is an identity plus this operator, and you can show that this plaquette, this U plaquette and U plaquette dagger, so this term will essentially go to del mu A nu minus del nu A mu whole squared, but I will be a bit more careful and I will not call these mu nu but rather ij's to emphasize the fact that this lives on a spatial lattice. This is a spatial plaquette where these del i's and del j's are del x and del y's, right, and del z's. So therefore, this is the magnetic field squared term, the B squared term, because you know this is a B magnetic field, so this is a B squared term, right? So this is the magnetic field energy of a gauge theory. You could also write, as we said, you could also write a term which I neglected last time, is an Ex squared, right, or E squared. That would have been the electric field energy term, right? In the case of spin half, of course, because Ez is electric flux is represented with Sz, this is just a constant operator, because spin half squared is just a constant, right? For spin 1 or spin 3 halves, it's not so. This will give you a non-trivial contribution to the Hamiltonian. Okay. So since we are dealing with spin halves, right, we don't have this term. We are not adding anything to our Hamiltonian. However, we can make the dynamics a bit more interesting by adding another operator, right? And this operator it will come up immediately. Is the following, that I take this plaquette operator and I square it. So what I'll do is that I have U plaquette and a U plaquette dagger, and I square it, right? So what does this imply? What does this mean? Remember that the function of this object U plaquette and U plaquette dagger was to rotate the orientation of the flux that goes around a plaquette. So if I have squared, it's going to do it twice. Rotate it and rotate it back. So now all this means is that if I have a state like this where it's going in an anti-clockwise fashion, if I add this lambda term on it, right, lambda times something, I'm just going to get back the same state, right, because it's going to rotate it to clockwise and then back, flip, right. It flips it twice and therefore it brings it back to itself. And similarly for the other term, right, anything else will get annihilated. So for example, if I have something like this, where it's almost going around but it's not, then this is not a flippable plaquette, and therefore this lambda term would not do anything to it. It will just annihilate it, right? This will be 0. Everyone is clear with this? Because this is going to play some role in at least the second part of the last part of the talk today. Yes.
Of course, as you pointed out, there are these AIs and AJs because we are living in a spatial lattice.
Yes.
But
Yes. Good. Thanks for bringing that up. So when you do when you want to write a partition function for this object, right, or a path integral, the way you start with it is that you say e to the power minus of beta h, as you would do for every spin model or every fermionic model you are aware of. But whenever you have a gauge theory, you have to project out. So this trace has to be done in a basis, and then you introduce all possible bases, right, all the possible states. However, you have to project out those states that do not satisfy Gauss law, and that is done through this projection operator. And the projection operator, and this is also what I discussed yesterday, that corresponding to this Hamiltonian, there is a Gauss law, and this Gauss law is simply the lattice version of divergence of E. Right? This is just saying that if I have a site, I can identify links which are going out, links which are coming in. I just take links which are going out minus the links which are coming in. So this means that in some of my notation, so these are plus x and plus y, right? And this is E3 and E4. Then the Gauss law in this case is simply E1 plus E2 minus of E3 minus of E4, right? Because this is my axis, this is my positive x and positive y. So when I do this, the projection operator looks like this. It's like a product over all of x and then delta of gx. So this operator will make sure that when I put the trace, any state that does not satisfy gx equal to 0 will get annihilated. And now what I have to do is that when I do this, I'll introduce a Lagrange multiplier, lambda, and then I will beta h, and then I'll have an e to the power I lambda of g of x, something like this, right? Sorry? Yes, yes, thank you. Right, so then there will be a trace which I have not resolved, right? So this lambda becomes the A0 after doing some gauge transformation. So this is where A0 lies, and A0, yeah, that's the answer. Okay, good. So we'll work with a Hamiltonian which has J and a lambda, right? And I'll come back to this so this is the part which I also wanted to say yesterday, but I could not. Yeah, sure.
Of course, you can emphasize that the J term and the lambda term do not commute with each other.
Very good. Yes. So I will emphasize this when I show the picture. Yes. Yes. Sorry, which one? This one? Yeah. So okay. So let's look at this then once more. So let's look at this, right? So what are the terms in the Hamiltonian? Non-trivial terms are this or this, right? This one or this one, right? Yeah. So this one is S1 plus acting on the first link, right? 1, 2, 3, 4 in my notation is going to annihilate the state because it's already up. So the first term cannot act non-trivially. The second term can act. S1 will be pushed down, S2 will also be pushed down, S3 will be raised, but S4 cannot be raised anymore. So this will also annihilate the state. And since this object is just square of this, it will do the same thing. So any states like this, which are 14 of them, will just get annihilated. This is something you can check.
So one thing, sir, is when we do projection operator,
Right.
so we are making this sure that we will take this non-trivial fluxes which are non-zero. So that's why.
Yes. See that. So okay. So the Hamiltonian already makes sure that you can only get two such states, right? But the Hamiltonian operates on a plaquette. Hamiltonian does not know what links are sitting here, right? The Hamiltonian only works like this. However, the Gauss law works on these links, right? It works on just for one case. If I'm allowed to use a different color, the Gauss law works on these links. So therefore, the Hamiltonian and the Gauss law serve a complementary purpose. Right? They are different objects. They don't reinforce each other. So the Gauss law selects those states where these four links have some well-defined values. Right? That's the divergence of E. So that's why when you are defining the full field theory when you do electrodynamics, right, in a Hamiltonian formulation, it's not enough to specify the Hamiltonian, you also have to specify what constraint, what is the Gauss law. Otherwise, your theory is not fully defined. Yeah. Right. No, you could not, you could have added the term, but it's a trivial term because it will commute with the Hamiltonian. So, yeah, but the toric code is a bit different story. So, because the microscopic model is not gauge invariant, it's the effective theory which is gauge invariant. Right? So that's a bit different. Yeah. Absolutely, yes.
Any constant that I want to put in,
Yeah.
I can use.
Yeah.
But I can also use this trick to relax the constant a little.
Yes, absolutely. You could do that.
Then
Yes.
does that give interesting features?
Yes, in fact, yes or no. I will comment on this slightly. Yes, but you're completely right. You can impose this, as Krishnendra is saying, not as a hard constraint, not as a delta function constraint, but weigh it with some e to the power minus of alpha gx squared, for example, right? The states, for example, which have a large value of non-zero value of gx will be weightless, right? This is one way to impose Gauss law, and in fact, this is I will mention this thing in a moment. Okay, so I will then now change gears to go back to the slide. But if you have questions about this, you can either ask now or anytime in the following.
The Hamiltonians of unit number they always commute because GX and
Yes, that's the important point, right? Because if they don't, that's why there's a local gauge invariance, as we said. Because the G commutes with the Hamiltonian, I can do a transformation at each local site with an arbitrary parameter theta. That's why it's a gauge theory. That's where the invariance comes from. Right? Okay. Okay, good. So, oops, sorry. Yeah. So, so then I come back to the slides, and in fact, a lot of it is the introduction can be completely skipped because yeah, we've most of the first day was talking about this. Again, this was all covered here, but I think the only one point I do want to emphasize here is that many of these ideas that we've been talking about in the context of thermalization and ETH has developed to a large extent, not only because of excellent theories and theorists, but also because a lot of experimental control has been achieved on many of these cold atom systems. So many of the ideas people propose can actually be tried out, right? For example, as you saw in the last talk today, in the first talk today, where this idea of scars was first checked experimentally in a PXP model, right? And in fact, then I should relate a comment of Krishnendra's, which is this way of, see, gauge theories is something we want to also study on quantum simulators because there are some problems in gauge theories like real-time dynamics. It's very difficult to study on classical computers, just as in spin models, right? Real-time dynamics spin models or fermions are also difficult. Same for gauge theories. The same reason why we want to study them with quantum simulators and whatnot. However, the point is that because you have all these constraints, it's very difficult to implement them on quantum simulator, right? Because a Hubbard model, I mean, in all it's a very complicated model, but still it involves hopping of fermions from one side to the another. So therefore, conceptually, it's more easy to implement than a model like this, where you have to make sure that the fermions and the gauge fields hop in a coordinated fashion, right? So also imposing these constraints are very difficult per se. So in many cases, people don't impose these constraints directly per se, but rather impose them in a weighted way, like the one I said. Right? So that's one of the ways of imposing Gauss law. Anyway, so let me just skip this through. This is just something that you have. So this is the model that I talked about. So this is Okin and so these are the two operators, right? So what is happening? Yeah, I cannot. Right, that's good. Good, thanks. So you have this operator, this O kinetic, which is the first one, right? The one that causes the flip, and the second is an O potential, right? And these names are very suggestive because O kinetic, what it does is that in the chosen basis of electric fields, it is a kinetic operator. It changes the state of this of your state, right? Whereas O potential is a counting term because it doesn't change the state of the plaquette. It's like counting how many flippable plaquettes there are. Just as a number operator counts how many fermions there are, for example. So this is the same role, that it just counts how many flippable plaquettes there are. And now, yeah, so this is everything that I have explained to you in much more detail on the blackboard. See, if you have a, so see, yesterday we talked about this, right? So suppose you have a hopping term. A hopping term is a kinetic term, right? Now, what does a hopping term do? If you have a fermion and an empty site, action on this term will make it empty occupied. Occupied empty goes empty occupied. So it changes the state of the, exactly like this, right? It changes the state. Whereas if you have a number term, C dagger C, it just counts, tells you whether it's 0 or 1, doesn't change the state. This is what the lambda does. That's why it's a hopping term and a potential term, right? Kinetic and potential. This is just a loose way of talking. Right. So and this is also what we said last time, that you have a Gauss law, and the Gauss law selects certain states. There are 6 of them in charge 0 sector. You can also make interesting theories if you restrict to other Gauss law sectors. So, for example, you can put charge equal to +1 on a site, and there you can show that you have to have only 4 states. This is again a good exercise which you should convince yourself of. Similarly, q equal to -1 is a condition which can be realized by exactly 4 states. Right? Just the opposite. I mean, you can take these arrows and flip them. That's what charge conjugation does, by the way, and you will see that these states map to the ones where q equal to -1. And for q equal to 2, it's very easy to argue that there are 4 links that are going out from a side. So you can have only one state. There's only one way in which 4 arrows can go out. All of them are going out. That's the only way. This model also has additional topological quantities. I'm not going to go to them. It's not relevant for what I say. Now, the other point I should mention is that if instead of putting, so remember I mentioned at some point that these models sometimes are also very effective descriptions of many condensed matter systems, right? So if you restrict yourself to divergence of E equal to 0, that is an effective theory of what are called spin ice compounds projected to 2-dimensional lattices. So spin ices are actually on pyroclores living on 3D lattices, but you can make simple spin ice objects by projecting the 3D lattice and put it on 2D. Let's again, this is just a comment and not an explanation. These models are the microscopic models for such systems, right? Then there is another class of models called the quantum dimer models, and they were proposed by Rockshar-Kivelson in the late 80s as to describe some special phases of antiferromagnets. And there the idea was that these electrons at a given site and electrons in the neighboring site will form singlets, and this is a non-magnetic state. And it turns out that such a model can exactly be described. The microscopic Hamiltonian is exactly the same as that of a quantum link model I've described so far, but with a slightly different Gauss law sector. You don't take divergence of E equal to 0, but rather you take divergence of E is equal to ±1. So you see, this is a staggering factor, -1 to the power x1 plus x2, which means that the sites which are in red, they have a +1 charge. The sites which are in hollow, they have a -1 charge, right? And they are staggered throughout the lattice. And you can show that you can map a dimer variable, right? Whether an electron makes a singlet or not. Anyway, this is just a comment again to state that this is a physically relevant model that has been of interest in the condensed matter community for over three decades now. And yeah, so this model will also show very interesting dynamical features, which we'll get to at the end of the talk. Right, and yeah, I'll skip this thing in the interest of time. So the first set of references, if you want to learn more about a Hamiltonian formulation of lattice gauge theories, you can go to the original first paper that came in this direction was in 75 by John Kogut and Leonard Susskind, where they talked about how to just write down Hamiltonians, fermions on a lattice, and gauge fields on a lattice. But that will give you the perspective from Wilsonian lattice gauge theories. If you want to understand the more pedagogically the kind of quantum link models I've been talking about, you can refer to this review by Uwe Jens-Wiese, which also talks about how these models have been or can be simulated in quantum simulators. Right? So in fact, some of these models have actually been simulated in quantum simulators. So that's an interesting point about this. I'll send the slides to the organizer, so you should have access to them. Good. So since we started yesterday by talking about Z2 and U1 gauge theories in 1 plus 1 dimension, I'm going to tell you about two scenarios, right? One is this disorder-free localization that people have looked at in the literature, not me personally, so I'm describing someone else's work, and I'll just try to say the facts and not go any further. And then the last part will be the weak ergodicity breaking. You've already learned what it is. I'll just give you an example of this scenario for these lattice gauge theories and transactionally invariant setups, right? So that's the plan for the last slightly more than half an hour. Good. So what is localization per se? I'm hardly an expert in this topic, so I will just mention some facts. So there is this notion of Anderson localization and many body localization. Anderson localization happens for a free system. So if you have a free particle in a random potential, so the potential is disordered, right? That's the language one uses. And if you are working in 1 and 2 spatial dimensions, then the wave function is localized for arbitrarily small disorder. Doesn't matter how small it is. Infinitesimally disorder will localize it, right? But for 3 dimension, you need a certain critical disorder strength beyond which the wave functions get localized, right? Below that it does not happen. And this is a statement about all the wave functions in the Hilbert space, not just any ground state wave function. Many body localization, on the other hand, deals or makes statements about systems which are interacting, right? This was a free system, this is an interacting system. So whether an interacting system localizes or not is a far stronger question. Here there is a proof, here there is no proof as far as I understand, and this is a topic which is being debated in the community, right? So one expects that for large disorder strength, these wave functions localize. But yeah, this is a hot topic of research, and other people than me can tell you about this, right? But this is just the notion of localization, right, which there exists. Now, so we needed to know this language of localization to understand what some people were doing. So one of the papers that came out about talking about disorder-free localization. So what does disorder-free then mean? So in the traditional examples of disorder, you needed to make the potential random in order to cause a localization to happen. So these people asked, can you observe disorder in systems which do not break translation invariance, right? You do not disorder anything, but can it still have localization, right? And right. So this is the paper. These are the authors. And they looked at this particular Hamiltonian, right? So see, you have a fermion hopping, and now the fermion hopping is attached to a sigma z, right? Whereas you have another term which very suspiciously looks like the Gauss law, right? Remember we talked about this yesterday. The only difference is that these people they're using a convention where sigma z and sigma x are interchanged to the convention I used yesterday. But that's okay, you can always call something sigma z and the other sigma x. So and of course, there's a Hermitian conjugate, which they don't write in the paper, but doesn't matter. Right. So notice the following, right? The following is the first term of the Hamiltonian states that whenever a fermion hops, the hopping is accompanied with a flipping of the spin that lives on the bond, right? Which is exactly the kinetic term of a Z2 gauge theory we saw yesterday. The second term, however, is an almost Gauss law, right? It's not really the Gauss law. Because to have the Gauss law, you would have needed the fermion number to be present here. It's no longer there. So it's an almost Gauss law. However, if you put h equal to 0, then the model has an exact Gauss law. H is 0, so therefore the Gauss law that I wrote down yesterday would exactly commute with the Hamiltonian, and therefore you could classify. There's a further symmetry, right? Which would in order to classify the symmetry, you would have to say the local charges, right, at each site, and that would specify your superselection sectors, and then you would do ED as we've been talking about. However, when H is not equal to 0, then that's no longer true, right? So this H term essentially talks between different superselection sectors, if you wish to put it that way. So yeah, it's not a gauge. That's right. Yes. So in fact, what they showed further that if you do a dualization of this model, so in fact you change some variables and write the model in a different way, this model looks like a hopping of a fermion. So this is just a Ci dagger Cj hopping, with a Hermitian conjugate. Now this hopping happens in a background, in a charge background, right? Which varies. So sorry, so this has to be J. I apologize. So this J changes from site to site, right? So this model maps exactly to a non-interacting theory which is embedded in a charge background. And this charge is exactly the Gauss law that I wrote down yesterday, right? So you have some sigma, well, I had sigma z's, but you have sigma x's and minus 1 to the power nj, which is 1 minus 2 times nj. It's very easy to check, right? So this model maps to a non-interacting model of fermion hopping. So what did they look at? So that's all the model is. So they looked at the occupation number, the differential occupation number of the fermions. So the fermion occupation at site j and site j plus 1 at any given time and you sum it over all the different j's, all the different sides. That's the first observable. They looked at something called the connected correlation function. So you take the fermion occupation at site L and then look at L plus J. Probably there's a summation over L, but they also look at L resolved values. Right? So this is a translation invariant object. And now comes the interesting point is that, so if you want to observe that there is a lack of ergodicity in this model, so the way they do it is that they take an initial state, right, and then they do a quench dynamics on the system, and they check what is the large time behavior of these observables we looked at, right? And in other words, whether they go to the same value that would be predicted by ETH or do the values change. So the initial state they take has you have to specify both the orientations of the spins and the fermions. The fermions are in a what is called a charge density wave or a number density wave. So you have occupied empty, occupied empty, occupied empty kind of setting, whereas the gauge spins, the gauge links are all pointing in an up direction, right? In the S I think in their notation it's the Sx equal to plus direction. Good. So and then the initial state they take is just a tensor product of this and this. But now the crucial point is that when you write such a translationally invariant setup, right? So this is the crucial point, that when you look at S and psi, they look translationally invariant, right? Of course, this is a translation invariance of 2, but that doesn't matter. So this is not disordered. This looks very nice. Translation invariant wave functions. However, if you were to resolve the fact that, incorporate the fact that this model is actually a model it's a gauge theory model, and this involves fermions hopping in a given charge background, you can resolve this initial wave function into an exponentially large number of states, each of which lie in a specified gauge sector. So that's what I mean when that's what they mean when they write out this fermionic this wave function, where psi remains unchanged, but these gauge links can now be resolved to lie in different Gauss law sectors. Right? So that, and then you have a sum over all possible charges. So you do and then you do a quench with an Hamiltonian where H is not equal to 0. Remember, this is the H term, and the claim is therefore that if your initial wave function is like this, you can resolve this into CQ psi q, where psi q is now a given wave function which lies in one gauge sector, in one Gauss law sector. Then the real time evolution of an operator will have will clearly not lie in one Gauss law sector, but will get contributions from different Gauss law sectors, right? And this mod of CQ squared tells you which are the different Gauss law sectors that contribute to the average. Yeah. No, it's not an even superposition. It's a superposition of all possible Gauss law sectors. Yes, with the same coefficient, I think so. Yeah. I think it's not. I think this coefficient probably stagger in distance up to of 2 or so. If you work this out, I think one can show this. So what they do is the following. So they look at 3 different objects or operators. So one is the memory of the initial state. This is exactly that row I showed you, and you will see that there are these different curves. And if your h is very small, so h by j is equal to 2. I apologize if you cannot see it, but please follow my stick. If this h by j is very small, then this line goes to almost 0. That's what is expected, if the system thermalizes. There's no differential distribution of fermions on even and odd sides. However, as you crank up the value of h, you see that there's a persistent memory effect like what was discussed in yesterday and the day before, that you have these oscillations, and these oscillations do not want to die down. Right? That's one of the observables they see. I'm just going quickly. Then there is something called domain wall melting. So what they have is that they prepare a domain wall state in which you have 0, 0, 0s and 1, 1, 1. So the fermion density is completely is a maximum imbalance. And what they're looking at is how this domain wall evolves as a function of real time. So in this case, the y-axis is the time. In this case, the x-axis was the time. and on the x-axis you have a spatial profile, right? So you have one color here and the other color here completely, and you would have expected that the domain wall goes away, the memory, the initial state washes off, but it does not happen, right? You see that even for very long times, in fact this band is, I think, is for 10 to the power 9 units in JT, this doesn't go away, it persists. So this is a strong memory effect. Similarly, you can also look at something about how these correlations propagate, right? So one typically expects that if there's a, if you have a model which shows ETH, you make a disturbance, and the disturbance then propagates in time, you know, and forms what is called a light cone. In this case, there is no such, you know, most of the weight is concentrated on the straight line. So there's very less diffusion into the system. So information does not get propagated, you know, to far ends of the system. So these are the kind of things they look at. In fact, they yeah, domain wall melting means the following, right? So you can do this problem in a fermionic setup. So take an initial state where all fermions, well, I make a cut, the left side has all occupied fermions, the right side is all empty, and you do a quench, right, with the hopping Hamiltonian, right? Just fermions, no gauge fields. What you will see if you wait for very long times, that this domain wall, right, the wall where you've completely occupied and completely empty, has melted. You will not see this separation for very large times. Fermions will be evenly distributed in the system because, you know, they are hopping around. In this case, it does not happen. That's the statement. Okay. Right. So now using the drop off of the correlation function, right, they are able to define something called the localization length, right? And as expected, you see that the localization length is, so if the localization length is very large, it means that the information is not localized. It is propagated throughout the system. But if the localization length is very small, then the correlation function decays very fast and information is restricted. Right? So as expected, you see that when H is very large, right, it has a very small localization length, which is another way of saying that the gauge, the different superselection sectors, right, are made more and more difficult. So they find it more and more difficult to talk to each other in the presence of large H, right? So you can think of it as if the fact that H is present, right, makes, yes, this is in real space, because there is J is a real coordinate and lambda is the real space. But this is true for an arbitrary excited states, right? I mean, they've looked at some initial states which are high energy states, right? So the stronger the H is, the more difficult it makes for different superselection sectors to talk to each other. Okay, good. So exactly almost a similar exercise was repeated by these people, but now they considered a U1 gauge theory, and yeah. So this is the Hamiltonian, and yeah. Right. Yeah, that is completely correct. Yes. So, no, the point is the following, that you're completely right, but the point is that in order to do so, your wave function also has to be contained in one superselection sector. If you are starting with a wave function which spills into various superselection sectors, the superselection sectors have different dimensionalities and Hilbert space dimensionalities. So now you are evolving it with a Hamiltonian, which itself is not, you know, gauge invariant. So the parts of the wave functions in different superselection sectors evolve at different rates, depending on the availability of the states in those sectors, and consequently the entire wave function, you're looking at the entire wave function, which is a sum over various superselection sectors. So it doesn't show any sort of ETH-like behavior or ergodic behavior. That's the thing that happens there. Also here, so this is a case of U1 gauge theory. The Gauss law is a bit more complicated. So the same that I wrote down, excepting instead of SZs, you have angular momentum states, and they look at they also look at imbalances and so on, but they look at the von Neumann entropy, right? And you see that the von Neumann entropy also has a very slow rise, and in fact they claim there's a log of time with which the von Neumann entropy rises, right? So this is one of the results. Now, a similar example was done in 2+1 dimension. I apologize, I should have written the paper. By Marcos, this is the result by Marcos Heil and his collaborators. I simply omitted, I'll put the reference in. And they also, so it's a two-dimensional system. So you have like an X and a Y axis, And what they do is that they arrange some things in the x direction, and they look at the correlations in the perpendicular direction, the y direction, and they see it as a function of time. And this is the correlation function of the electric fluxes, right? Sz and Sz. And you see that this correlation function has a modulating behavior, which even though it decreases, doesn't really completely go away. Good. Now there are other references about this gauge theory and ETH, statements about ETH in gauge theories, and these are very serious works by these authors. I encourage you to have a look at them if you're interested. Good. So now in the remaining 20 minutes, I'll focus on the work about so in this work, which was done in collaboration with Ornob Shen in the audience, and also Shoptoshi Bishesh, who was a student from ISER. We looked at gauge theories, so U1 lattice gauge theories, pure gauge theories in 2+1 dimensions, these systems, and we have resolved all Gauss laws, right? So there's no conundrum saying that there's a wave function which spills into various Gauss law sectors. So you specified the Gauss law sector into either the quantum link model Gauss law sector, where you say divergence of E is 0 at all lattice sites, only 6 states are available, right? Or the quantum diamond model, where the Gauss law is specified to be -1 to the power x, and that's it. And so these are two distinct sectors, and they will never talk to each other. The wave functions, of course, we restrict ourselves to these Gauss law sectors, and we mean translation invariance in that setting. There's no breaking anywhere. Oops. Right. Good. So now that we have back to translation invariant settings, we should quickly remind ourselves about the symmetries of this model. Some of them have implications. So you have the usual point group symmetries of the square lattice. So you have lattice translations, you have rotations, you have reflections. Then you have what is called a charge conjugation, which I've discussed before. So a raising operator goes to a lowering operator. U goes to U dagger goes to U, and electric flux goes to minus of the electric flux. Now it turns out that in addition to this, if you put lambda equal to 0, right? So you don't have this particular term present. So just have the J term, which just flips the plaquette. Then in addition to this, these objects, you can write on another operator, C, and then this C is a product of these electric fluxes along a line. Oops, sorry. What did I do? Okay, yeah, so let me just, so if you have a lattice, right? So you have all these lattice links, and you can take a product of the E's, right, along a given direction. So that's what that C operator means, right? And so at lambda equal to 0, you can show that the C operator anticommutes with the Hamiltonian, which means that the energy will be a degenerate, at least doubly degenerate energies, right? Any non-zero value of lambda, any non-zero value of energy has a partner at -E. Except for, yeah, so this is the statement. However, at lambda equal to 0, it turns out that this model will have an exponentially large number of eigenvalues. And this is a consequence of a theorem that was proved by Schechter and Yadekola in this paper, that, yeah, 0 modes, energies at equal to 0. Right. So this is an exponentially large number of 0 modes, and this is what we call as an index theorem, right? And you can see this illustrated in these figures. So you have two different lattices, right? One is at Lx equal to 10 and Ly equal to 2. So this is a large, like a torus where one extent is bigger than the other, and the other where you have an almost rectangular system with 6 cross 4. And then you see the density of the states. So rho of E is a function of E, and at E equal to 0, you see this peak, right? So that's the thing. And you can represent this by this, mathematically you can say that you have an alpha, you have a delta function at E equal to 0, plus you have a regular term of the density of states, something like this. Yeah, the index theorem part was, so I don't remember the exact statement, but the statement is, but the idea is that if you have a lattice Hamiltonian, right, where you need at least one symmetry under which the Hamiltonian is invariant. In these cases, you have, like this reflection, like I have drawn these axes Sx and Sy, and if you reflect the Hamiltonian around these axes, it is invariant, right? So it states that if you, as long as you have these point group symmetries and you can construct this operator C, which anti-commutes with the Hamiltonian, then the total number of zero modes, then the system will have an exponentially large number of zero modes, but the exponential goes as the linear dimension of the system. I think it's a linear dimension, right? So even if it's a volume, it's probably L and not L cubed. Anyway, that part I don't remember. But if, as a volume, So if it's a 2D system, it will go as L square. 3D system will go as L cubed. Yes, that's the point.
This plus one-dimensional model.
Yes.
So here, how does this means this code means this interaction between two neighbors? So how they block each other? That depends on my lattice size because this Lx and Ly, when I'm using this 4 and 6 and so on, this triangular or two.
Sure. Yeah.
So whether this interaction means my
No. See, I mean, don't confuse this with it's a very simple case, right? When you talk about spin chains, right? You have a hopping Hamiltonian, S plus, S minus. You never ask the question how big my spin chain is, Lx is, right? It just is the basic unit block is S plus, S minus, and whatever L can be 100, 200 or 10, that many number of blocks are present, right? So the basic build, that's why I focused on basic building blocks, which is the plaquette. A lattice, whatever it's 10 cross 10 or 10 cross 2, will have either 100 or 20 such plaquettes. And those are the interaction blocks. So the basic interaction in a spin model where you have an S plus, S minus is a two-body interaction. Here it's a four-body interaction with four spins talking to each other. So that remains unchanged, irrespective of how big the lattice is.
in that case, whether I have to consider the next neighbor or not means that.
So what do you mean? You mean I make the interaction strengths bigger? Is that the question? So then you could also ask that if I have a spin model S plus S minus, why don't I write S plus S minus S minus or S plus S plus S minus? It's an equivalent question, right? Sometimes it can change the interaction completely, sometimes not. But the most obvious things we write down are hoppings involving two particles, right? That's the most basic things. Here you cannot write anything to do with two objects because that will not keep this gauge, it will not keep this larger symmetry present. So here the smallest object we can write down has to involve four links or a basic closed loop, and the smallest closed loop you can write down on a square lattice is 4, on a triangular lattice is 3, on a honeycomb lattice is 6, and so on. So that's the point, the smallest interaction you can write down. If you had fermions present, it will be 3. You would have 2 fermions sitting on the lattice size and the link in between. That's the way we construct models. Right? Good. So right. So what happens is that this model is non-integrable, and you can check this by, for example, plotting this level spacing distribution. Again, let me not go into it. The model has very interesting ground state physics. Again, let me not go into it because we are talking about excited state physics. So we have a system. So let's see in what sense does the model displays some interesting high energy dynamics of physics. So let's take a system where you have an Lx like this and your Ly is 2, right? So of course, like most of the choice of the lattices in this case is restricted by how big a calculation you can do. In this case, if you want to access all the dynamics, you have to do an exact diagonalization, and this limits how big a lattice you can take because these computations are exponentially expensive in the lattice size, right? Right. So in this case, what we are looking at is the first thing we are looking at is the von Neumann entanglement entropy, right? So you know what the von Neumann so you have a density matrix, right? And the density matrix can be split up into two parts, one belonging to this LA subsystem and the other is LB subsystem, right? And then you take the trace of one of the subparts and then you do a rho log rho, right? By what has been said, and then you look at this the entanglement graph for the von Neumann entanglement entropy. This is a half chain entropy, which means that the chain hasn't split into exactly equal halves. Right? Technically, this is you have to be slightly careful when you are cutting and gluing this because it involves a gauge theory and a local constraint. So you have to do this a bit more carefully. But yeah, but conceptually it's very straightforward. Now what you see is the following. Right? You have three sizes being shown here. One of lattice extents like in X, 8, 10 and 12. Right? And in all three cases you see the behavior you would expect of a system which is ergodic, in the sense that you have you have or following ETA. So you have the lowest energy states which have low entanglement entropy, and then as you go higher in energy density, remember I'm plotting the E by L, right? The entanglement entropy increases, it peaks and then it comes down. Right? In all three cases you see this, and more importantly you see that as you increase the lattice size, the peak goes up, and the peak, and so this is roughly proportional to this ratio of the lattice sizes, right? That's completely as expected, for any interacting theory, excepting that you see that there are these states, mid spectrum states. So with an energy density which is macroscopically different from your ground state, which do not seem to scale. They seem to be invariant, or they have the roughly the same entanglement entropy. So this tells you that there are some anomalous states, and as per the definitions that we saw in the previous talks, at least here they don't become exponentially large. So this is a case of a weak weak breaking of ETH.
It was peak around
Yeah.
-1.
Sorry. Yeah. So this is just because. So what is the peak around -1? Sorry.
Actually, here we are considering just -1 in the lambda, so we are
Yes.
just adding this subtracting one this potential.
No. So you can so you have so you see you need one scale to set the problem. So J is set to 1. Lambda is a parameter which you can change. If you change lambda, this thing will shift, and I'll show you a figure like this in a moment.
Just wondering whether when the spectrum state is at lambda equal to -1.
Yeah, that has to do with the fact how the mix.
Energy equal to -1. Sorry. Is there a shift?
There is a shift. I'll show in the figure plot after this. Okay. So it's not only just the von Neumann entanglement entropy, but rather you see this in other objects, other observables as well. You can look at this Shannon entropy. The Shannon entropy will also show this difference, right? You have this usual ETH satisfying states, and then you have some scars which are extremely different. And notice the scale, right? So remember there's a log here, and this number is 10, and this number is slightly less than 3 or almost 3. So there's a huge difference. You can also construct this correlation function of the electric fluxes, and these electric fluxes are just these E's which are the electric fluxes in the vertical direction, right? The ones that are pointing. So we look at this correlation function, and even there you see the presence of these anomalous states here. Right? In this case, there are exactly 4 of them. So now comes to the question that you're all wondering. So if I take Lx equal to 10, right, and the same lattice size, and I change the lambda. So the red one is at lambda equal to -1, the green one is at lambda equal to -0.5. What happens is that, of course, this curve shifts, this envelope shifts, right? But the important part is that if you isolate a state right here, you will not be able to draw a one-to-one correspondence with the state here with the state here. It's typically a superposition of exponentially large number of states at this point. Not for the scars. For the scars, this is just a vertical, this is just a horizontal shift. Whatever these states are, right, the wave function of the scars does not change, right? What do I mean by that? You can take the scar wave function, take your computational basis, and write the scar as summation of Cii, where I are the states in the computational basis, and you can look at the amplitude of these various Ci's, right? And you see that this is the computational basis, and you see that the wave functions do not change at all. Whatever they were at -1 is the same at lambda equal to 0. So the wave function of the scars do not change as you tune the lambda. Right? So they are behaving in a very predictable manner in this sense, whereas these states are absolutely not. So that's what I mean. The scar states are determined at 1 lambda and fixed for all lambda not equal to 0. What happens at lambda equal to 0 is a bit more tricky. I'll come to that. So what is happening here? So what is happening here is that you have a localization of these anomalous states. The localization is in Hilbert space, right? Because normally you would have expected many of these states to contribute to a typical eigenstate, which I'll show, but the scars don't. And in this case, the scars, this is denoted by QMBS, they happen to be eigenstates of both the kinetic and the potential operators. So they are eigenstates of this operator as well as eigenstates of this operator. And this is what makes these scars very special, right? So the O kinetic acting on the scar states annihilates them, whereas if you add this particular operator, which is just counts the number of flippable plaquettes on the scars, then you get an integer value times the same wave function. This counts a number, and then this number is an integer, which tells you that the states that contribute in the scar wave function all have a well-defined, not only well-defined, but the same number of flippable plaquettes. Otherwise, NF would not be an integer. Right. So you see these scars, which we call type 1 scars, and type 1 scars are just the scars. They are identified by an integer value for O potential and 0 value for O kinetic. And these are scars in the quantum diamond model now, right? I've talked about the quantum link model. The Hamiltonian is the same. It's just the Gauss law is different. And you again see the presence of type 1 scars in quantum diamond model. And now you see how striking these scars are, because if you look at the wave function of a close by non-scar state, so a state that would satisfy ETH, you would see that the contributions from all these different basis states, right? So they're almost like slightly less than 20,000 of them, like 18 or 19,000 of these states, and you see all of them contribute with some amplitude, right? You see this. However, for the scars, it's very, very nice. Only 4 states contribute with amplitudes of 0.5, right? And that's it. In this case, only 16 states contribute, but these two have a different value for potential. Here is 4, this is 7, and here is 8. So these kinds of anomalous states start appearing in your spectrum. So what happens at So let me try to quickly say this, and then I'll go ahead. So one way to understand this behavior is what we call in the paper is it order by disorder in Hilbert space, right? So when you have an Hamiltonian and you put lambda equal to 0, right? So the Hamiltonian essentially only consists of the J term, no lambda term there, and then the Hamiltonian is just O kinetic, right? And then following this theorem that we just mentioned, that there's an exponentially large number of exact 0 modes, O kinetic, so which is the statement that these eigenstates of O kinetic, are 0. They are 0 eigenvalues. So these 0 modes themselves, however, are very excited states. They have they spread themselves over the entire Hilbert space, so they are locally thermal. That's the statement. So here you see an example, right? You look at the Shannon entropy S1, and you are looking at this at lambda equal to 0, right? You don't see any special anomalous states here, whereas the anomalous states, the presence was expected, at a value close to 3, if you remember. That's what is being indicated by this horizontal line. All the 0 modes, they are living here, right? And in fact, if you zoom them up, this also shows the importance of that this is an index theorem, that these 0 modes, they are slightly protected, so they don't mix with these non-zero modes. There is in fact a tiny gap, right? So as we have kept on saying, you have a many body system with exponentially large number of states. So if you go to any non-zero energy, right, or energy like here, the states are exponentially close to each other. But the 0 modes are protected, so they form a tiny gap from the other states. However, if you now turn on a tiny value, if you turn on this operator, right, this lambda term, what happens is that this lambda term stabilizes certain combinations of 0 modes. So there's an exponentially large number of 0 modes, but certain particular combinations of 0 modes are stabilized. And it's the modes that are stabilized are called quantum scars in this way of thinking. So this is sometimes what happens in at least I think it was Villain who in the context of spin models who talked about frustrated spin models who talked about order by disorder. So if you in frustrated systems, what happens is that your ground state has an exponentially large degeneracy, right? Because the particular constraints don't stabilize some ground state. However, if you turn on a certain interaction, the interactions will stabilize the linear combination of all these many exponentially large number of states, and a certain order establishes itself. So something similar is happening here, but this is happening in the Hilbert space, right? Not in the possible states of ground states. Can I have 5 more minutes? Okay, I just wanted to say something interesting, and then I go on. Right. So thanks a lot. Right. So yeah, so this is what we call order by disorder in Hilbert space, and also it's interesting that you can now ask the question that I have stabilized the scar state. How so? Clearly, there's some linear superposition of these zero modes which give you the scar state, and you may be interested to ask, well, what is this? What is the amplitudes of them? And if you look at these amplitudes, I think much to Arnav's and my surprise, this curve is very indistinguishable from if you had a Monte Carlo simulation. If you look at a Monte Carlo simulation and you look at how these phi's are changing from one side to the other, they just look very random. Or pseudo-random is a better word because everything is defined here. But this graph is remarkable. Anyway, so this also leaves an imprint on the real-time dynamics. So if you look at, for example, if you look at a bunch of initial states, right, which have the same energy density, so so you look at this particular number of if I'm interested in states with an excess energy density of this number, so volume by 2 times lambda, for one particular system size, you see that there are so many initial states, but only 18 of these states have an actual overlap with these quantum scars. And now what you can do is that you can take different states. So these two lines that I have drawn, they have similar values of energy density, but very different values of this operator that I am plotting. Right? This is the correlation function of the electric fluxes. Right? They are very different values because they start from somewhere here and somewhere here, but they don't have any overlap with the scar. So this follows exactly what you would expect from ETH. So even though the initial values are very different, because the energy density is the same, they lose memory of their initial values very fast. I mean, well, of the same time scales. That's what is important. And they go to the same diagonal ensemble, same value which would be predicted by ETH. The scars, these states, however, don't do that. So if you take another state with the same energy density, but now it has an overlap with the scars, right? Then they go to a different final value. Right? So this leaves an imprint on the real-time dynamics like this. So yeah, so there are other different scars in this model. So type 1, type 2, type 3, I do not have time to explain all of them. However, I will just end by pointing to the existence of extremely simple scars, which we call Lego scars in the quantum diamond model. And they turn out to be really, something that you can play with. So in the quantum diamond model, the way we arrived at this conclusion was rather convoluted and non-intuitive. But once you have the results, they are extremely aesthetically appealing. So you have a quantum scar, which is a superposition of only 4 such Fox states, right? And notice that, so this is the quantum diamond model, right? And which means that you have a staggered +1 and a -1 charge on the lattice sides. And you see that the way that these states form, this is a anti-clockwise, this is a clockwise. Whereas this object again is in clockwise and anti-clockwise. So you have 4 possible combinations, and now this should immediately lead you to think that what if I start forming, what if I start, I make a cut of the system, right, along this horizontal AH, and then I think of a linear superposition of, so this is an anti-clockwise clockwise minus clockwise anti-clockwise. This should remind you of a singlet, a spin singlet, up down minus down up. Right? This is a piece which we call a Lego, and you have an exactly similar piece, another Lego L2, and you can just tensor these two objects. So you have an L1 tensored with L2, and this will give you 4 states. Right? So these are the very simple interpretation of these, not interpretation, it's a nice way of writing down these states in a very close packed form. And it turns out that there are more and more of these kinds of Legos. So you have simple Legos and also more complicated Legos, right? And you can essentially play this Lego game to construct more and more involved types of quantum scars. And in fact, so let me just end with one last comment. In fact, once you have this construction of a Legos, at least more than one types of Lego, this should allow you to argue that there are exponentially large number of such states in the thermodynamic limit, because even in the example that we have chosen, right? So imagine you take Lx to infinity. So this means that the simplest system you can form, the simplest scar you can form is by alternating two Legos, L1, L2, L1, L2 and L1, L2. But now you have the option, you can form another Lego by taking out this object and replacing it by something else. So locally, as long as you have more than one choice, you can build an exponentially large number of such states. Right? So of course, this exponential may not be enough to defeat the exponential of the states that come up when we satisfy ETH, but there's a macroscopically large number of these states, right? So that's, I think, is an interesting result. Right, so there were many open questions. We know more about the model now than when we started, but this is the point where I will stop, because I hope I have given you an introduction or at least a flavor of gauge theories, what gauge theories are. They're highly constrained, and there are various interesting kinds of high energy physics that you can explore in these models. Yeah, so with this I'll stop. Thank you for listening. Thank you for your questions. Yeah. Right. Right.
Everything is degenerate and
Yeah.
so does lambda just practical it does just practically when it is the zero energy substance, or it also connects to some state outside the substance? Is there anything that is forbidding?
No, I think this lambda will only connect to the zero in the subspace, in that E equal to 0 sector.
If we turn on lambda, then the index theorem is gone.
There's no.
The zero modes with the non-zero modes. So there are all kinds of matrices. So there will be all kinds of, and at the end of the day, you
So yeah, okay. Right. So sorry, I misunderstood your question. If you say zero modes and non-zero modes, they do talk to each other, right? That's right. Yeah. Yeah. Not that we know.
so it's very interesting. So it's a game. We haven't completed the game. You can have bigger and bigger and bigger Legos. So the Legos are more rectangular, but they are nonetheless finite.
Yeah.
No. But see, suppose you have a super long Lego. To know that it's violating ETH, you need to go
Very large. Yeah.
Nonetheless, it will violate right?
Yeah.
Tensor products can never be so high.
Yeah.
Understand that. But I'm just saying that you need to go to a much bigger length scale.
I mean, the way these Legos are constructed, if you play around a bit with this, you will see that the moment you try to act the Hamiltonian on these objects, right? So these Legos are shielded by what we call the inactive zones or the dead zones. So there's no excitation. So there's a quantum interference, destructive interference, which prohibits the excitations from propagating outside the Lego. That's the kind of the way you can construct them like this. That's one way to. Yeah. Yeah. Then you can do that. That's yeah. So then you can do that. Right.
Is there some algebraic understanding?
So these are the singlets, right? So you can. So there are more complicated objects like these fatter objects, right? They're not singlets. They are kind of. So I think it is in principle possible to take these and make Ly equal to. So this is Ly equal to 4. You can make them Ly equal to 8, and then you can try to think of coupling singlets and try to form a state which will. We haven't done this exercise, but it's a very interesting exercise that one can do in principle.
There are no more questions. Let's thank.
Thank you.
Okay, so last time we were looking at these constraints that come from symmetries essentially on matrix elements of the form which are relevant for discussions of thermalization, but these are asymptotic formulae, and these are also true in some average sense. Okay, however, because this directly relates to OP coefficients, it has brought there is some give and take between this imposing thermalization constraints and consistent conditions of conformal symmetry. So the bootstrap program in CFT is essentially imposing this set of infinite constraints. So this is the crossing equation for 4-point function, where you have external operators I, j, k, l, primary operators, and so one can decompose these 4-point functions in terms of these diagrams, where there is this primary, there is a sum over this p index. So this O you may not be able to see, but this O carries an index p, and this is summed over, and so p and all its descendants is exchanged between these two legs in this diagram. And this is a expansion in a particular channel, and due to the fact that these OP coefficients, they satisfy associativity. So I could have chosen to do OP between I and j instead of doing OP of I and k. Yes. Yeah.
These constraint equations,
yes.
basically actually this equation that you have
Yeah.
yeah. Does it depend only on the Q matrix of the CFT, or does it also depend on which CFT?
With CFT, so this is going to, this will not be satisfied for random numbers Ci, j, k. Yeah, so these bootstrap those numbers which define a CFT. And it will also not be satisfied for random conformal scaling dimensions of the operators. So this is an infinite set of constants, and that will allow you to search all consistent CFTs in the space of all CFTs. Yes. Yeah. No, this is not a Feynman. No. This is.
So here does anything tell me that this OP is talking to OI and OJ? So does it
Yeah. Oh, so so holography actually builds this in. So in holography, this really becomes Feynman diagrams, which are called Witten diagrams. So these are Feynman diagrams in ADS.
So here it doesn't mean that OP and OI and OP need to have some symmetry, so they couple. It's not that.
No, they couple in the sense that this will be non-zero, this number. So it's like the algebra, the OP coefficient will be non-zero. And these actually become if the bulk is defined by an effective action, that becomes the bulk coupling. Yeah. For the CFT, yeah. If I think of, yeah, these essentially, yeah. So these are part of the data of the CFT. These numbers, Ci, j, k, l. So for different CFTs, these numbers will be different. But these are, so one point to realize is that there are infinite of these constants, and the goal of this bootstrap program is to find all consistent numbers which satisfy this. A bootstrap is precisely this, the entire thing that I just said. So it's the program to figure out these numbers such that this equation is satisfied. Okay, so there are complicated functions associated with this P, and there is a sum over P. So there are infinite such equations. Okay, and people have. So it turns out that even at times, so this is again dimension independent, this equation, and it turns out that people can do also some analytic conformal bootstrap. So there are some dispersion-like techniques where you can find some sum rules for these OP coefficients. And those are also done in some asymptotic limit. Either you take very large conformal dimension or you take very large spin. And there are some results. So it turns out, so recently people have started exploring what a theory which would thermalize give me. So people have started using this equation. So this is an equation where I'm again looking at a 4-point function, but I have taken two of the operators to be heavy, especially the operators at 0 and infinity to be heavy. So this can be thought of as a, by state operator correspondence, as a light 2-point function in a heavy state. And if it's sufficiently heavy, then I should be able to approximate it by a thermal state if it satisfies constraints of thermalization, and then I should be able to write this as a thermal correlation function. So which is known, which one can estimate in a CFT. And this will also give me, and now this left hand side I can decompose into these numbers, Cij. So this will also give me some equation forCij's, which I can try to solve. And it turns out that the things that I get actually match with theCij's that people have found using these analytic methods. So this have been recently shown. So last year there have been some papers where they showed that this large spin bootstrap and this thermal bootstrap give consistent results. So it's just saying that so the bootstrap constraints are consistent with the constraints that you expect from thermalization, especially if you take the asymptotic limits. Which is why also this quantity in 2D CFT, this was matching what you expect from ETH. And this statement I am saying is in general CFT in D dimensions. Yeah. Yeah. They can be real numbers, so people know regions where they have to be, or they know some rules aboutCij's. Yeah. Yeah. No, heavy limit, heavy limit and large central charge. So this is done in this large n in n equal to 4 super Young-Mills. So you have a holographic dual. That is true. So this is the Zhiboedov-Dodelson paper. Okay. So this was about, this was just some connect from yesterday. Today we will look at these 3 things. First I will talk about a more non-local probe, which is comparing reduced density matrices. And then we will see that the failure of thermalization is due to the fact that there is some integrable structure in all CFTs. And why central charge plays an important role, large central charge, why it plays an important role. And then we'll I'll make some comments if I deform from the CFT.
Maybe it's a vague comment. Suppose I
Yeah.
just look at the transfer speed as
Yes, yes.
that's of course an integral property.
Yes.
So of course if I look at each matrix and look at that time,
It will not satisfy.
it won't
Yeah.
satisfy it. But if I just average over them or just look at some, let's say
Yeah.
some vague notion of typical eigenstates
At very high.
formalized, then it does satisfy it.
Yeah, I think same thing, because also the Ising CFT, if you look at very high descendants and you do averaging there, you will satisfy that constraint. But one non-trivial point is that if you get rid of the descendants, so Ising CFT will never satisfy this constraint. But if you look at C greater than 1 CFTs, then there are still heavy primaries. Those will still satisfy this if you average over the primaries. So you get rid of the Virasoro symmetry. Still there is a statement. Yeah.
Do you say that CFTs are integrable because they have to satisfy those?
No. So one can derive the integrability. I will sketch the step. Yeah. So it's a integrability of the KdV hierarchy, which all CFTs have. And again, it's due to the presence of the stress tensor. Okay. So the trace distance will be a distance between 2 density matrices. So this is the reduced density matrix of a pure state, and this will be for us a heavy state, which we will assume to be this something in the middle of the spectrum and with very close by states such that it satisfies this ETH like constant. And then the other state will be a is a thermal density matrix, and we are tracing over the complement. And what we want to compare is, okay, and also we want to choose this temperature by matching the energy. So this equation can be solved in a CFT, and this sets that ETH temperature, which is that saddle point temperature, which this is just telling you that if this conformal dimension is large, then temperature is large, beta is small. And then what we want to compare is this quantity. So I take difference of these two density matrices, square them, and take trace over it. And in Ising model, in the non-integrable version, so there was a paper by Grover and Gaddison, where they plotted this quantity and they noted as a function of subsystem size over total system size, it seemed to follow a power law. Okay, so of course, this is a pure state, and this is a mixed state, like psi and e power minus beta h. But of course, if I take the trace, this also becomes mixed, but they can never be equal. So there will be some deviation that you will start seeing as you increase the subsystem. But how the deviation grows as a function of the subsystem, that from the Ising model plot seem to follow some power law. Here, so they looked at states in the middle, for which they can match one-point functions of local observables. Okay, so then this object, if I write it out, I will have trace A rho A psi square, which is the secondary entropy, and I will also get a trace A rho A psi rho A beta term, a mixed term. And if I write the path integrals in CFT, so this psi, this is a pure state, so this is CFT on a cylinder with psi is inserted at far past and far future. So this is the state, so this is rho A psi square, this is rho A beta square, and this is trace rho A beta rho A psi. And these are connected because I am multiplying two density matrices, then taking a trace. Okay, and this region is the reduced region. Okay, and these are the terms that appear, and it turns out that there is a technique due to conformal symmetry, again, which allows us to compute these partition functions. So it allows us to get rid of this tube by basically, it's like insertion of, so if we look at this diagram, so it allows us to resolve this tube in terms of operator insertions. So it's like a complete set of states I allow, because everything can propagate between these two through this tube. So and these are specific coefficients which can be again determined by conformal symmetry. So one can determine this, and then what one gets. So what one gets out of this is, so if one writes it out, so this trace distance takes the following form: sum over k1, k2, psi ok1 psi minus o beta, and then the same thing with k2. And this is sum over all operators with this coefficient c k1, k2. So what appears is exactly the deviation from thermality for all expectation values with a metric which is set by also the operators. But this is sum over all operators, and this appears essentially because you see that when I get rid of this tube, I have two correlators. One is a 3-point function on the cylinder, which is this term, and one is this 1-point function on the torus. And and then based on this sum, I can partition this sum into two sectors. One as a universal sector which will be present in all CFTs, and one which will be dependent on the because the universal sector is essentially the identity and its descendants. So the stress tensor and higher powers and so on. And the other will be the primary, the sum over the other sectors. So this gets, so I can, and it turns out that these are the behaviors of the two sectors. So the non-universal sector, there is an exponential suppression. And this is essentially because of the asymptotic formulas of OPE coefficients that we derived. And the universal sector is only suppressed polynomially in central charge. Okay, and the universal sector comes from essentially operators of, so this n indicates operators of this form, sorry, operators of this form, t power n normal ordered. So stress tensor and higher powers and its derivatives, but polynomial means it's like OPE of many stress tensors. So this is polynomially suppressed. So in large C, so you have to be at very large C for these two density matrices to be close to each other. Non-universal sector is sensitive to those results of OPE coefficients. Okay, and this actually can be tracked back to contributions. So in this K1 K2, so this K1 K2, the contributions coming from some integrable sector of the theory, and there are infinite of them. So the quasi-primaries in the identity module, which and there is again the state operator correspondence. So every operator has a corresponding state. So the states of the operators which are in the universal sector, they can be arranged into some integrable hierarchy. So that is the KDV hierarchy, which is this Korteweg-de hierarchy, and that had already been noticed in the 80s, that all CFTs in 2 dimensions have this integrable structure. And I will just briefly sketch how this integrable structure appears. Yes. Yeah.
So if this is integrable and you still get this e to the minus s by 2 suppression, you could have calculated those random RNNs.
Yeah.
Which of course you cannot because you have averaged that out here. Those random RNNs couldn't have been Gaussian. They would have some long tails or something. Is there a way to see that?
But still, I mean, still this large C means means if C is very large, then this integrable effect is very small. Yeah. So for example, so I can tell you another calculation. So for example, yeah, very small compared to so what will happen is, so in general, because it is integrable, one should write a GGE with all these charges, and those chemical potentials will be small compared to beta for this very high large primaries. And also there will be C will play a role in them being small.
But if one
Yeah.
could have calculated those arguments somehow, and still the distribution could be Gaussian. It will look almost Gaussian, but it will not be Gaussian.
Yeah, yes. Because it is because you are saying because of this structure. Yeah. Only for 2D. CFT is there, it's there. In higher dimensions, the n equal to 4 has been proved, n equal to 4 super Young Mills has been proven to be integrable, but that is some other hierarchy. Yeah, so in 2D, how this appears is this indirect. In large n, large, not, large SUN's gauge group large n, it's known to be integrable. Where so if one takes into account 1 over n corrections, then recently there are studies which show that there, in some sectors, in very high energy sectors, there can be some kind of chaos. Some kind of chaos, like level spacing statistics and so on.
Sorry, this
Yes. No, large N. Large N, and then you can tune the entire range of the tooth coupling. Yeah. You can solve by Bethe answers. Yeah. But I think even for some sectors, even you can go in 1 by n orders and you can still find some integrable spin chain, which determines the anomalous dimension. So. Open. Yeah. That tooth coupling, tuning the tooth coupling. Yeah. You can compute the stringy corrections. Okay, so coming back to 2D again. So it turns out that every CFT, so this is some work from 80s, admits this Feigen-Fuchs representation, which is also called the Coulomb gas representation, in terms of these fields which admit free expansion, like oscillator expansion. And so here this central charge is hiding here. So if I just use the canonical commutators, I will be able to derive the Virasoro algebra, for example, from this representation. And the central charge will be related to this lambda and h bar in some way. So this is a representation which is useful to get to the KdV. So then it turns out that in terms of these fields, I can construct some vertex operators and write down a Hamiltonian, write down a theory whose classical limit, so classical limit here corresponds to C going to infinity, because h bar goes to 0. So, yeah, right. And then in the classical limit, that theory becomes, in terms of these vertex operators, becomes the Singe-Gordon theory. So there is a theory you can write down in terms of these phi's, and this theory you write down, h bar appears explicitly in the Hamiltonian. But still you can take h bar going to 0, you get the Singe-Gordon. This is one particular theory, I have not written it. So this has KdV integrable structure. So basically, in this theory, from the phi field, you go to this u field and you go to a v field. So there are some non-local transformations here. So you go, so basically from phi you can go to this v. So this is called a mu dot transformation. So this v, if you look at the classical equations of motion, it satisfies this PDE. This is the KdV equation. Okay, so this derivative with t, this is 3 derivatives with sigma, and this is 1 derivative with sigma and v. But this equation, actually this system, this Hamiltonian system is integrable, and you can find infinite polynomials of v, which integrals of which will define KdV charges, which will all commute with the Hamiltonian and with themselves. So those are the KdV charges of this system. Yeah. Yeah. Cos h. Yeah. Instead of.
It's very interesting that it's KdV because KdV is almost analogous to Bethe integral. And if it's a Bethe integral thing, then your RMS can be almost Gaussian, but not.
Oh really? I see. Oh, I see.
Anyway, but maybe that's the.
Okay. Okay. Maybe. Yeah. 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 So for some explicit models, one can check. For some theories. Yeah. Yeah. The data, so T plus has the data of central charge. So no, this is the identity sector. This is only the identity, universal sector, only central charge appears there. Yeah. This is true for any CFT, this. And then the connection to CFT, so now we are in this classical Singe-Gordon model. So it turns out that if I now, So this d and this beta, these are the quantum analogs of that other classical thing. It turns out that t plus is mu transform of u. Because if you see the t plus, so t plus involved this, exactly this kind of a transformation, where u is this d phi. So then, so now polynomials of t plus, you integrate and you can find the KdV charges. At least you know the classical KdV charges. And one can then work, so it turns out that, okay, so one condition is that all the ln's have to commute with this vertex operator. That will fix this parameter beta, which appeared here, in terms of central charge. And then all these polynomials of this integrated form the KdV charge. And there is no closed algorithm to find the quantum KdV charge. You have to work level by level, make sure everything commutes. So classical KdV charge, there is an algorithm. But for these quantum KdV charges, I think people have constructed only till level 16. And they look like this. So the first one is, of course, the Hamiltonian. The second one comes from t square, integral of t square. It gives this particular object. And then next you get this and so on. Okay, and then these, so these operators which are not suppressed, which are 1 over c square suppressed, are precisely these operators. One can organize them in terms of these operators. So, okay, and then there are many open questions like, what are the characters? Like, how do you calculate the partition function with this generalized KdV? And then there's a question like, for example, for L0 we know it is counting partition of integers, integer partitions. This is actually looking at more finer structure, what kind of partitions, and so on. So, for example, this one can actually show that this counts partition into triangular numbers, some special numbers. And this is some other more finer and so on. So if you have to specify everything, you essentially specify the entire partition, the entire microstructure. So these are not worked, all these things are not worked out. These are all open. Okay, so yeah.
One way of seeing third is that the image level chart you can accuse in product of various and
Yeah.
other some.
That is true. That is true. That is why this appears with power 2n. So this is that power law. So this is that power law which Tadun and friends saw. L by L to the power 2 delta. So for Ising model, you can try to match these things with their plots, if you are at the critical. This is due to Virasoro symmetry, just because of Virasoro symmetry, just property of the stress tensor. Because everything is fixed by the Virasoro symmetry. That's why there is no way to get rid of this if you are in a CFT. Okay, so now I will, so then there are many open questions here. Okay, but now let me move to deforming the CFT. Yeah. In CFT or conserved stress tensor, what do you mean? CFT with a boundary. You still have Virasoro. So these charges will be there. These charges will be there. No. This is just from the Virasoro algebra, nothing else. They can be done, it gets very tedious. So it's open problem to find a better algorithm. So this has been done by Zamolodchikov. Okay. So going to this out. Okay. So now because we had some introduction to quenches and out of equilibrium dynamics. So one can ask what happens if I subject a CFT to out of equilibrium dynamics, and because CFTs are associated with some universal properties like critical exponents, can we see some universalities when we subject a CFT to a out of equilibrium dynamics. So one thing to do, or maybe this is probably the simplest thing to do, is to suddenly go to a CFT or suddenly go away from a CFT. So by tuning a coupling to the critical value. So this is, say, the critical value. This is, oh, so this is G minus GC, so this is 0. So you tune it to suddenly to this 0 at some time t equal to 0, which is also tau equal to 0 Euclidean time slice. So if you look at the Euclidean CFT, it starts from here. So there is a boundary for this Euclidean CFT. So a reasonable guess will be to put a conformally invariant state, a state which preserves conformal boundary conditions, which is this boundary state. And this is the proposal, and then people have checked it and found corrections to it by Calabrese and Cardy. But once you make these ansatz, that you put this boundary state and you have to, this is not normalizable state, so you have to normalize it and so on. But once you make these answers, then you can calculate quantities, because now you are evolving with a CFT Hamiltonian, and you know how the Hamiltonian acts on this state, and so on, and how operators evolve. So for example, if you want to calculate entanglement entropy, so this is the half chain entanglement entropy in the Ising, transverse field Ising model at criticality, and this shows evolution with time for different amplitudes. Sorry. Yeah, so different graphs are different heights of this h minus 1. Yeah, Quench amplitude. So you go to higher and higher thermal values. You saturate to higher and higher page values. Yeah. It is some gap state, and then you quench to suddenly to a CFT. You could do a reverse. Yeah, but then, but here I am calculating time evolution with a CFT Hamiltonian. That's why I am quenching to a CFT. And these have been matched with exact solution of the Ising model. So this ansatz works well for this. And this is essentially CFT on a strip, and you can associate again a temperature to it, which is the temperature with which this value saturates. Then one can try to do the smooth kind of quenches, and then only under very restricted regimes one can justify sometimes using linear response and then get some scaling of measurements of operators at the critical point with this rate of the quench. And then these have been also verified in some lattice models. Okay, so there are some universalities associated with quenches, and then so this in the literature is called the fast fast scaling. So essentially, if the quench is smooth, there are at least two regimes one can think of. So again, one has this G as a function of time, but now it's smooth, and it goes from some initial value, asymptotic initial value, and it saturates, say, suppose, to some other initial value, final value. And it is changing. There is some characteristic time window over which it is it has this maximum amount of change, which is this. There's some time, and if I can do a derivative expansion, this will be like the slope of the function at small times. So this is t over delta t. So there is some time window over this is changing. And so this rate, so the rate of change is delta inverse. So this delta inverse, of course, needs to be smaller than the UV cutoff or the inverse of the lattice spacing, which is not the case for sudden quench. Sudden quench, delta t is essentially 0. when I'm doing the sudden quench. So it's unphysical in that sense, but of course analytically more tractable in many cases. But so realistically, this always needs to be maintained. And suppose I start with a theory which has an initial mass gap. Let's call it m naught, m of g initial. So then there can be two kinds of regimes. In one case, this delta t inverse can be larger than this g initial, or there can be this case when delta t is even smaller than, delta t inverse is smaller than this. And this is where you are expected to maintain adiabaticity, because this is small, and maybe there are other scales also. But of course, if the coupling passes through a critical point, then we will break adiabaticity. So in this regime also there are some universal scalings which go by the name of the Kibble-Zurek scalings. So scalings of, basically scalings of measurements at the, so you measure things within this window, and more specifically after the point adiabaticity has broken down. So within the, so within this window there will be another window which is, there is some scale associated with this, where adiabaticity will break down if suppose say the critical point is somewhere here. This is a G critical. So no matter how slow you do it, you will break adiabaticity. So then if I make some measurement inside this, then there are some scalings even in this, even if I do it very slowly, and these have some scaling which depend on this critical exponent, the scaling dimension. So this is a non-equilibrium, this is a thing measured in non-equilibrium, but it still captures some property of that critical point. And this formula, so this formula is valid when this is just smaller than the UV scale, because essentially then there are no scales for this theory. So it basically sees the UV fixed point. So conformal perturbation theory essentially captures those scalings, but these are still not very rigorous methods, because this is still perturbative using linear response. Yeah. No. So this power will be this fast quench power. This is what will come from linear response. This is almost dimensional analysis, the linear response formula. But it can be shown with the CFT calculation. So you calculate the retarded Green's function, evaluate it within the CFT, UV CFT, and do the integrals, you will get this power. But then actually, to find the exact formula, one has to resum the perturbation theory, CFT perturbation, then maybe one can find the interpolating plot. So in various lattice models, you can, where you can tune this delta t and solve the problem exactly, you can fit your plots to this exponent in the first regime and to this exponent in the slow regime. Yeah, please, yeah, please, yeah.
It's a bit of trick here. Once you do it in a lattice model, typically do this with a bi-axis system.
Yes.
And there, the system length inverse
Plays also, yeah, the scaling functions.
Yeah, because you see, it's all two-body problem. Two-level problem if you are at a really fast, slow level.
Yeah, yeah.
Because it's whatever else scale.
Landau's inner
Landau's inner type of stuff.
stuff. Yeah.
So that has to be
Yeah.
taken care of.
Yeah. So in thermodynamic limit, you can
Dynamic limit is
match with this. Yeah. So yeah, this problem is also kind of open to how to really interpolate between these things. And there are also other scalings associated also with the amplitude So there is, I don't think there is an argument why that should be the case. So here the intuition is that all the so these are words which I've seen, that all the dynamics is frozen and system doesn't have time to react basically. Yeah, that's Kibel-Zurek diabetic arguments.
Here, of course, you can take an argument that
Yeah, by the UVCFT fixed point.
but it's not clear that
Not clear, no. Not clear. Okay. Okay, so but so to I think to address all these is more systematically, probably one has to take a step back and go to path integrals for general quantum field theories in out of equilibrium. For example, quenches is a way to do this, to take it out of equilibrium, and then in these time dependent path integrals, we will be forced to work with these folded contours, because we don't know what the final state will be. So we can only calculate amplitudes where we come back. So we only know how to compute these in correlation functions. But once we have these contours, so these are contours which are slightly separated in imaginary time. Once we go to these contours, complications increase, because now we have to actually double the fields. And because we double fields, now there are new kinds of correlations between these copies. So for example, there will be a correlation because we are starting with the initial state here and there is a turning here. So for example, because this contour is turning, one has to identify this field here at this time slice with the field here. So that will, these boundary conditions will induce non-trivial correlations. So then on these contours, then one has to do field theory essentially, and then look at how these amplitudes behave. So these are the relevant contours in out of equilibrium and in quantum field theories in general. And then, of course, the main question is how to develop a theory of critical phenomena in out of equilibrium by doing what we do in field theory. We look at observables and then we find that there are divergences, so we have to renormalize, and that tells us if there is a critical point hiding somewhere in the space of couplings. So what are the corresponding statements now? So I will just end with some questions now. So I'll end much quickly. Yeah. Okay, so if you do this, so we have done this, and some people have also, means that there are many literature, many scattered literature, Krishnananda will know. So if you say if you just take 5-4 theory and quench the 5-4 coupling and calculate composite operators renormalization on this Schwinger-Keldysh contour, then you will see that you will generate new kinds of counter terms. And these new counter terms will be now time dependent, because they will depend on the derivatives of the coupling which you are quenching. So there is extra scale to write down new counter terms. So for example, if you do that, so say I started with this kind of a quench where I just quench this operator, this one operator, and I do this quench at some scale mu. And then I try to calculate the counter terms, and then I will see that this counter terms will renormalize all my other operators, and all the other operators will also start flowing in time, because through this coupling G1, which is function of time, these other couplings will also become time dependent. Okay, so as soon as I move away from this scale mu, so this is like one RG condition, that at this scale mu, only G1 is time dependent, others are not time dependent. So if I move away from this, then my theory will tell me what function of time the other couplings have to be. Only then it can be renormalized. So this suggests that there is now a 2-parameter at least, because this is some function of time, a 2-parameter running of the coupling. So there is mu, of course. So one can, there are many ways probably to develop this. So one suggestion could be that, so now instead of trajectories, now there is a 2-parameter family. And then the question is, can we have a critical phenomena also in this time? And maybe there are indications like people have looked at these dynamical quantum phase transitions, Loschmidt-Echo, where there seems to be some kind of divergences at times. So can these be understood more systematically, these critical phenomena in time? And then of course, if there is, then what kind of CFTs do we get? Or do we at all get CFTs, or just or what do we have there? Okay, so I will conclude. Yeah. Yes. 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 Yeah. Yeah.
Here there is a problem because the point is that you cannot really view the quantum current.
Yes.
You cannot really go beyond the scale of 1 over 10.
Yes.
Because,
That is
after
true.
that,
Yeah.
nothing doesn't come.
Yeah.
So it's not entirely clear that even if such a critical point exists, you're going to capture it
By perturbative.
This is also beside, another point beside the point
Yeah.
in most of these kind of cases is that
Yeah.
the drive term is, what do you call it, relevant.
Yes.
Then it takes you away towards the strong coupling fixed.
Right. In most
Even
examples.
within the flow up to this 1 over del,
Yes.
see that the flow is going towards this.
Oh, I see.
So, I mean, at least in some models.
Some models.
So it's not entirely clear, how.
If one can find.
So it is universality and out of equilibrium. Whether
But
it all exists,
in large N, can one do non-perturbative things? So that will be a question.
I don't really know. Because you start with a Kelvinish and one thing is certainly true, you generate these extra operators and all
Yeah.
that, but that's there in standard RT also.
Yeah.
You generate other point. But the other point is to regulate this 1 over
1 over delta T.
That's not usually easy. I don't know how difficult.
So large N, are there examples where?
So I know some examples of doing what they call as non-perturbative RT. But those are in condo-like systems, where this non-equilibrium is like applying a potential difference across this condo system. It's not in the sense of making things
Time dependent. I see. Okay, so this is definitely to be understood. Okay, so I will just conclude. So from what I talked about, so there is some nice cross-fertilization between bootstrap ideas in CFTs, going back to CFTs, and thermalization, and demanding a CFT to thermalize is consistent with these infinite constraints of bootstrap. So the theory allows for thermalization to happen, and this presumably has some implications for gravity through holography. And of course, means as we saw that if we look at these asymptotic formulas for primaries, we have some shift in the central charge. So those are some predictions for bulk quantum gravity corrections. So this is one line of development why these ideas of thermalization are important in CFTs in both ways actually. And then this last some words I said, these folded contour quantum field theories, so they remain largely unexplored. So also if one has to calculate this out of time ordered correlation function, then one has to consider even further folds in the contour. If you have to do it using path integral. So in general, these folded contour field theories are unexplored because they are quite complicated, because you have to deal with many different kinds of propagators. So number of diagrams you get increase automatically. So and then this is this last discussion. So if there is any systematics that can explain these scalings, that will be a very important development. And maybe using holography that can also address black hole collapse, similar kind of non-equilibrium problems in gravity. Okay, so these are many questions in these things. So I finish with this. Thank you.
Okay, thank you, Vikram, for getting us started. And for the first time, we have time for infinite number of questions. So yeah, we'll start with our
Hopefully not infinite. Yeah.
So you mentioned that the could be CFT, the integral, and people have also done some Day3 kind of things. And this large C regime, only the sort of first example that is feature matters and the others are small. But suppose you move out of this regime, then I also program for DBI and understood or misunderstood. I don't know that. This thermalization also has implications in terms of some black hole picture.
If you move out of what are the implications of those charges? Yeah, yeah, yeah. There are some quantum hairs, so there is some discussion. Maybe he knows it better. No. I think there in quantum gravity there can be these hairs, these scalar hairs. So there is a paper. This is also debatable. So there is one paper I know by Ian DeBoer and others. So, but he tries to connect to these hairs of black holes. So these test tensors are like they are dual to graviton modes and these are boundary gravitons. So this is like these charges are like condensate of graviton modes. So. Yeah, that is true. That is true. Yeah.
Then the black hole will just be covered with hairs.
Yeah. Which diagram? The first diagram. So here this is not coming from any action. So there is no relation basically. There is no question of difference because there is no relation. So these are so this is just a symbolic way to represent OP. This two operators. You are taking an OP between two operators. So these are not coming close in space or anything. So you are expanding in cross ratio, which can be not related to them coming close in space time. In Euclidean space, this is so you can ask what is the radius of convergence of this series. Okay, so that depends on so that has a good answer when the cross ratio in one channel is smaller than 1 and in the other channel the cross ratio is close to 1. And cross ratio, if you remember, was this x12, x34 over x13, x24. Right? So that ratio, if it's closer to 0, then it makes this side of the expansion a convergent expansion. If it's close to 1, then that tells you should use this channel. Okay, but people have proved that these are convergent, and also you just by demanding convergence also you can get some some constants. So that it's a useful question in that way. So. Yeah. So no, for the Cohen-Pfeiffer theory, at least so people have calculated it up to 3 loops. So they can renormalize by bringing in some new counter terms. So there will be counter term higher loops. So it's called quantum quench at one loop. This paper, but they have calculation till 3 loops, and then they also do for the Yukawa theory. Wilson like, yeah. 3 loop, so 3 loop Schwinger-Keldysh contour, 3 loops using Schwinger-Keldysh propagators. Yeah. Perturbative RG. Perturbative RG.
There is one proposal really said that presence for event horizon and there will do some tricks to, and actually not do the full finger Keldysh not coded contour calculation, right? By Honglu and others. So I was wondering, so the trick is really simple. I was just wondering whether that helps.
In holography. Oh, this geometry, this double geometry. Yes.
Instead of doing all this,
Yeah. But is it known means why it gives the right answer? No. That is.
it is known that it gives you at least
Yeah.
expected answer.
That is true. Yeah. That has not been explored in quenches at all.
But can that be done? I mean, kind of trying to answer some of the questions that we have posed.
Maybe holographic RG kind of calculation.
Yes. What happens to
Yeah.
function of RG?
Maybe. I don't know. Not thought actually. Yeah. So are there any calculations of, there are correlated calculations.
Correlated calculation, yes. That is something I guess you I don't know in this context.
But that is also with a cutoff or
That's more or less
standard. No,
maybe something clever is going on, but for example, can we see mixing of
operators.
operators in the way you mentioned?
Yeah, there will be new kinds of mixings now. And the coefficient of the mixing will depend on time now. Operator mixings will be time dependent. So that is a new effect. In this. Yeah, might have those features. Yeah. Yeah.
Suppose there are several ways of doing non-perturbative RG on using quantum parameters, but of course quantum parameters not having real time. But then there is this another method which is mostly pioneered by the people Heidelberg. It's functional normalization.
Yes.
The ones that you say, I guess, are not those.
No. Yeah, I know, but I have not read those. No, they move the time, right? The turning point they keep moving. So. Yes. Has some. Yes. That is the paper I saw. Yeah. And they showed. Yeah, there yeah. And I remember their process involved decreasing the turning point. This turning point of the Keldysh contour. Heavy. So in large central charge limit, so these conformal dimensions are dimensionless numbers, and central charge is also dimensionless number. So this delta H is much larger than C. The conformal dimension is much larger. That is it.
In that case, how can you say that will be?
That we have shown last time. They satisfy these ETH like constraints. So then that makes this a reasonable expectation.
Are there any other questions? Not this, and for a bit. And we'll reconvene at 4.
Okay, great. So this is the last talk today. Well, we have 2 minutes still. Maybe I can just start writing and then I'll write slowly. So what I intend to do today is basically sort of tell you some of the things that we have been discussing, but in a more gravitational framework. In particular, ADS CFT. But like many things that I have said so far, this will also be primarily sketches, not derivations. So you may not be completely happy with some of the things, but in view of time, that's the best I can do. So let me begin with the following statement that, as we have learned, ADS is essentially dual to a CFT in various contexts, and we want to capitalize on this. So it's only natural to consider specific states which are interesting states in ADS. And by states in ADS, I mean just some geometries that are solutions of Einstein's equation with a negative cosmological constant. The same equation ADS itself is a solution of. So we want to consider states like that, and one particular state is a black hole state, which has been confusing people for a very long time, and for many reasons. In fact, black holes are nowadays extremely mainstream, even outside, I mean, this kind of studies, but that's another story. So let me start by telling you the metric, for example. Incidentally, this is a metric, or some variant of it, is the metric that was written by Schwarzschild more than 100 years back when he was on a war front. He found the first solution of Einstein equations, which Einstein himself did not believe in, but anyway. So that's the simple thing. Where f of r, this f of r is a function which is 1 plus r square minus some constant mu over r to the d minus 2. I should have said that this is in d plus 1 dimension. And as you can see that this mu is just a real number, so therefore f of r can be 0, and as we all know that the event horizon, basically what you'd look at is when the function in front, sitting in front of dt square goes to 0. So f of r equal to 0 defines event horizon, and from the expression it's obvious that there is a solution for this equation. So therefore this geometry has an event horizon. This is called the Schwarzschild black hole. And I want to heavily rely on this today. Just for completeness, consider, at least for today, d to be bigger or equal to, in fact I should have said 2, yes, 2. D equal to 2 is very special, which is also visible in this formula. If you said d equal to 2 here, this goes r to the 0. So that's a bit special, which is already visible. Now, yeah, maybe there are some parameters I should give. So this parameter mu, just for completeness again, I'll erase this in a moment. This is 16 g Newton times mass of the black hole divided by some constant, some number that depends on the dimension, multiplied by omega of d minus 1, which is basically the volume of the d minus 1 sphere. That's again a number. The only thing that you really need is the fact that this formula tells me that if I keep mu fixed, m is 1 over g Newton. That's the only important thing that I will later use. Okay. So pictorially, there are many reasons why this has been confusing, but instead of going into that, let me draw you a picture. Now, as you all know that this is a solution of an equation for general relativity, and as we all know that general relativity is space-time coordinate invariant theory of something. So therefore, this is and since this metric is written in a particular coordinate, there might be a better coordinate or more suitable coordinate to describe the geometry. So instead of writing down the coordinates and how it is related to this, which everything that you can find in a textbook, for example, let me draw you two pictures which you will also find in the textbook, but add two very small additions. So truly the simplest picture that you can think of is a picture of a square. That's it. So these wiggly lines are singularities which are inside of the black hole so that we don't see it. These ones and these two as well. These dotted lines are essentially event horizons, and these lines, so these vertical lines are the boundary or the conformal boundary that we have introduced before. So this is where, if you wish, the CFT lives or defined on these vertical lines. Okay. And you can ask at this point, where does time flow? Or rather, how does time flow? How does the CFT time flow? It will become clear in a moment. And I'll come back to this picture again. If you ask this question, it turns out that this picture and the geometry allows you to define two choices which are not equivalent. In one choice, you have time flowing on the upwards, on both right and left boundaries. In the other choice, time flows upwards here, but time flows downwards here. Or vice versa. You can pick the other configuration as well. Okay. So basically it says make the following thing, that t is equal to some tau on right on r. By r I mean this boundary, and this is equal to minus tau on left, for example. So if you wish, I could, so you see that this choice in these two different diagrams will look different, right? That's what I wanted to say. So, and then the point is, if I want to do some sort of quantum mechanics in this space time, then I need a Hamiltonian. So R is right, L and L is left. So there exist two Hamiltonians corresponding to each of these time choices, two Hamiltonians. And let me just very quickly tell you what they do. Two commuting Hamiltonians, I should say. One is following: I del t left on a state gives you h left on that state, and if you have I del t on r on same state gives you HR of psi. Okay. So, these are really the two choices which we can do. Now, let me get back to this picture and draw your attention to the following thing, that it looks kind of odd because simply because we started with a discussion of a black hole, which is like, I am watching a black hole and I see that there is some event horizon and that is that, right. But if I look at this picture, it tells me that, let us say this one, I have an observer here, but I also have an observer here. At least we like to believe that there is no clone of us in any other side of the universe. However, they may exist without a causal correlation. But this geometry, this is just a geometric fact. I didn't have to do anything. This is just a coordinate artifact that told us that these are solutions. Such squares are solutions of Einstein's equation. So, let us take them seriously. You might say that, okay, I don't want to take it seriously, and that is fine. But suppose I do, then the question is, what does it teach us? And it is as good a solution as the single-sided Schwarzschild black hole is, right. There is no reason to disallow one or prefer one from another. And that brings us to a concept which is very central, and I will introduce it in a moment. It is called thermofield double. So, this is a concept that has existed very long. I think I don't exactly remember since when, but in the context of black hole, this was first realized by Israel, maybe in the 70s, I might be wrong, but later Maldacena made very interesting observations. I also forget the years. Actually, he keeps making interesting observations, so dot dot is probably not bad. So, let me define what it is. It has nothing to do with a black hole. So, given a quantum mechanics, I can do the following. So, yes.
There is no communication between the left and the right, right?
Yes.
Any field in any quantum field, so you will have zero correlation between the two.
That's correct.
That is
correct.
So no information exchange.
That is correct, but there is yes. Short answer is certainly yes, but that if you think about throwing in something here from the right boundary, certainly this object has no idea about anything else. Similar object, suppose I throw it in, once they go inwards, then they know.
Right. But that an observer
Outside you don't know. Never access it. Yes. Absolutely. Okay. So, given a quantum mechanical system, let us make two copies. Make may not be the right word, but anyway. I am not suggesting you avoid the no cloning theorem. It is not that. It is just take two copies of the same quantum mechanical system that I am allowed to, right? A particle in a box, another particle in a box. That is all. That is all. And then the thermofield double state, I will define a slightly restricted version of it, which you can generalize a bit more, but nonetheless. So, e to the minus beta En by 2, n left tensored n right sum over n. So, n left, n right are basically energy eigen basis for left and right, etc. And there is some weight factor which I have chosen to be to the minus beta En by 2, but you can choose it to be something else. It's perfectly fine. So, yes. Oh, I should have mentioned En is the eigenvalue of the nth eigenstate with respect to the Hamiltonian.
both right and left have the same.
Yes, that's right. That's right. That's why I say they make identical copies of two Hamiltonians. Yes, indeed. Everything. Take your favorite quantum mechanics, just take it twice. Do the same problem on 2 pages. That's all. So, 2 basic facts. I shouldn't say 2 facts, maybe 2. Anyway, 1. So, you can define the density matrix TFT, which is nothing but this TFD, right? Oh, I should have also introduced, you see this parameter that is here, it's some free parameter which I am allowed to set to anything. It's just something that I can write. So, this is clearly the density matrix, but if you do this, a little bit of algebra will tell you that rho square TFD is equal to rho TFD itself. So, this is a pure state, blah blah. That's fine. No wonder there. Now, property 2 might seem a bit more interesting, is that suppose I do a partial tracing of this density matrix. So, I define a rho which is trace over, let us say, left degrees of freedom of rho TFT. What do I do in that sum? I will just get rid of all the left degrees of freedom, right? You just take the trace, insert complete basis and do the sum, right? Only over left degrees of freedom. This will give you e to the minus beta h r. So, clearly, so let me also call this rho beta. So, this implies rho beta square is not equal to rho beta. It is a mixed state. In fact, it is thermal. This is one of the first things we write down as the thermal density matrix, right. So, the point is, the reverse is also true, of course. Given a thermal density matrix, I can always devise a thermophile double state whose partial trace will give me that matrix, right. In other words, in some sense, you can think of a black hole which appears as thermal as a part of a pure state, and this is how I treated the pure state to get to the black hole state. That is all this means, at least for now. Yeah.
When you are writing the state, aren't you introducing a correlation between the left and the right?
They are entangled, but not correlated.
They are entangled.
Yes. Yes. So,
That doesn't imply non-zero correlation.
no, I mean in the sense that I can do independent things here and here.
This may be a dumb question, right?
Yes. Is some complicated correlation. I agree with you. But on the so if I did not mention entanglement, what would you conclude? Are they correlated? No, right? Yeah, that's all. That's all I am saying. Yes.
Proposing things like this, then aren't you introducing a correlation? Because otherwise, when the density matrix become mixed,
I agree with you. Yes.
one has to.
Yes, yes.
Yeah, okay. You are saying that in this step 1, where you use QFT, you are not like multiplying density.
No, no, no.
That's the whole point.
You are not multiplying, but this is not what we normally call correlations. But because this is how, I mean, well, it's a terminology thing perhaps, but it's like literally taking, I don't know, preparing 2 spins here and then. Exactly. So that's how they are correlated. Yes. Yes, I agree. Yes, yes. Yeah.
Are you allowed to do that given that there is no information exchange?
That you mean whether I am allowed to write down or interpret the black hole state? Yes.
This thermophile double state.
Mhm.
As if, I mean, so if I knew that there was no information exchange between these two observer at 2 points,
Yes.
can I think of a state which is entangled between the two?
I think yes, because even in EPR pair, for example, when we write down an EPR, this is like an EPR pair, right? A very fancy one. So an EPR pair doesn't mean that I can send signals that way. So that's why I said it's not correlated but entangled. Correlated in the sense that I can actually send signals to affect the other.
It seems similar to the explanation you gave yesterday, right?
Yes.
After about scrapping and how one would reconstruct.
Yes.
So that if one had a reference state,
Yes.
then just by knowing some small.
Making measurements on that.
It's like saying that left and right maybe they're two very different things, but if there's some.
They're literally like EPR pairs. So yes, you are right. If I make the spin of one, I know the spin of the other. Doesn't mean I can send a signal. So that's what I mean by this. Exactly. So yeah, yes. Good. So pictorially,
So again, a very dumb question. So
yeah, go on.
TFT like a macroscopic cat state?
I do not know what a macroscopic. Well, I know what a cat is, but is that what you mean? Yeah.
Okay, suppose we talk about this singlets or EPRs.
Yes.
I mean, of course they're entangled, right? But the basic bits are still like one-bit objects or something.
Sure.
I mean, here you have this NL and NR. You have like many bits here and many bits there.
No. NL is purely on left. It doesn't know anything about NR. So you see, when I write down NL, as I said, I mean you tear 2 pages on your copy, you solve one quantum mechanical problem, you again solve the same quantum mechanical problem. The 2 pages do not know about each other. Yes. Sure.
Oh, then it's okay. Then there's something probably unnatural about it. Because okay, macroscopic cat states, whatever they are.
Okay.
They don't satisfy your cluster decomposition theorem.
I am not talking about cluster decomposition yet, but anyway, I mean, this is just any quantum mechanics. TFD is a very standard construction. It's nothing. Yeah. Okay. No. So, are you asking whether there is any consequence on cluster decomposition on the TFD? I don't know. I would be tempted to say yes. I think so. So simply, I'm saying the following thing. I do quantum mechanics in this room. I do.
So you're saying it satisfies cluster.
Yes.
Then it's fine. Then for me it's a physical.
Yes, but I don't know how to prove that. Yeah, sure. I think it does.
You can write certain other kinds of states which again look like this, which don't satisfy cluster.
Oh, that may be true. Yeah. No. This is just garden variety stuff. There's nothing fancy here. I mean, it's very, very standard. One step that you have to take from here to here is to make this identification that this is something like this, which is not standard. I mean, which is not obvious. It needs a bit of thinking, and a bit more thinking allows one to do some things on these TFD states in view of these black holes, which I'm going to at least sketch. Okay. So, well, yeah, I'm not doing bad in time. So this picture, sorry, I always get this picture wrong. I don't know why. So I should really get only one side when I do the partial tracing. So this is, if you like, trace of L. That's just a diagram, nothing more. I don't have much to say about this. Now, if you accept this, then I'm going to do stuff to the TFD state. So suppose I have the TFD state. Oh, before doing that, I should just make one, I think, important comment. At least to me, it is important. So whenever we sorry, whenever we write down states like this, we are not we are not mentioning how you arrive at this state. Meaning, what is the initial condition on which I will evolve my equation of whatever, in this case Einstein equations, that will eventually give me this state. So, there is always a possibility that these states are actually never reachable, starting from a ground state and a reasonable initial condition. So, this possibility I do not think is ruled out. So, whatever I say or whatever people say is contingent on the fact that these objects exist at least in some approximate sense, and they are called, that is why they are called eternal, because there is no time anywhere really. I mean, I am not talking about formation of this, I am accepting it. So, as if it always exists. So, hence the word eternal. Okay. So, now let me go back to this. So, in the context of the black hole, so if I have an eternal black hole, I am going to do some very simple things. One of them is the following. I am just let me look how much do I want to say. All right, let's keep ahead in a bit. So, for example, you insert, let us say, an operator OR at the right boundary. This is my right, yeah, this is my right, this is my left. So, I insert an operator OR. This should have no knowledge about this. So, therefore, OL and OR commute, right, because they do not know about each other. But for some reason, I want to measure the expectation value, measure some OL expectation value in the state which is disturbed by OR. So, what do I mean by that? You compute this object TFT 1 plus epsilon OR. I'll mention in a moment what exactly I am doing. But what I am imagining is that this deformation comes with a small coupling or small parameter which I call epsilon, and therefore, any change. So, this, if you wish, 1 plus epsilon OR times TFT is basically TFT tilde. In general, it would be an exponential, but since epsilon is small, I can only keep the leading power, and this is the deformed state, and in the deformed state, I am measuring OL, right. This I can expand. Plus, let me get the number right, 2 epsilon OL OR in the original TFT state plus higher orders. This is the answer. So, this I do not really care that much about. I can also assume that this is 0, it is some operator whose one point function is just 0, let us just not worry about it, but I want to keep a tab on this. This is a 2-point function you see on the TFT state, right. And in ADS-CFT, this can be computed. This is computable in ADS-CFT. And the way roughly you do that is very simple. You have an operator OR here, you have an operator OL here. So, imagine that operator OR is inserted, some things happen to the TFT state and blah blah blah. Eventually, I am just computing OL OR correlation in the same state. So, what I am supposed to compute is basically a geodesic that connects to points, which can be done. Yes. Yeah, this is where I am coming to. So, let us not decompose it right away. Let us write it this way, and let us use ADS-CFT to compute this, see whether it is decomposable or not.
No, I understand that, but the TFT state.
Yeah. So, the TFT state just ensures that this commutator is 0. It does not tell me this is 0. Well, no, not quite. You know, see what you are doing here, geometrically, it's kind of clear, right? These two are independent as so, okay, let me put it this way. So, okay, what I mean operationally is that this commutator and its expectation value is 0. That doesn't mean this is 0. That's what this, yes. Yes, yes, I agree, I agree, I agree. That is there hidden. So, yes, good. So, what you have to, so why does this proposal work? That to answer that question, first you have to show some things. For example, if I do a CFT calculation of a 2-point function like this in a TFD state, and I do a geometric calculation whether they match or not. The answer is they do. Well, they don't really, but the answer is not 0 in a CFT. In other words, so coming back to your question, this is once I establish that there is a non-vanishing correlation, you might say this is not a local theory anymore. That's what this means. But it does satisfy cluster decomposition in the usual sense. So what is the upshot? Yes.
Why this model area, this calculation of this 2-point function side of it, this gives me a geodesy.
Oh, there is no explanation really. It's a statement about of ADS-CFT that if in ADS-CFT you want to compute, let's say, a 2-point function like this, you can make this statement more generally, but let's make it in the context of this. Then you see ADS-CFT tells me that all correlations are basically some geometric objects. So what is the geometric object that I am supposed to compute? The most natural object is the geodesic that connects the 2 points. So let's compute that. And that that will give me this expectation value. And this I can compute in ADS-CFT because also I know the metric. It's just a geodesic calculation which is very simple. Yes.
So if my black hole was completely classical,
Mm-hmm.
you know, this horizon was completely opaque, so I cannot.
Yeah.
So this thing is still non-zero?
No.
No, right? So
No.
this is some effect that.
Yes, yes, yes. That is in, yeah, implicitly there. Yes, good. So let me give you the result and draw your attention to what it alludes to. So the result is if you do this, geodesic calculation, which is not hard, that we can compute, and I told you already how time evolves. Let's take this picture for the time being, just for simplicity, let's say, not getting things confused. You will find the following. Find that OL, OR in TFD is going to be some e to the minus a t over beta. That's a problem. Why? Because at large time, t goes to infinite, this correlator goes to 0. And we know, this is a CFT calculation, I haven't exactly shown you, but I also told you last time, I think, that in a CFT calculation, you do not expect a 2-point function to exactly vanish at t much, much bigger than beta, right? So this will be true, t much, much bigger than beta. This is problem. Why is it a problem? Because my CFT is telling me it should not happen. My gravity answer, which is very simple, is telling me it must happen. It's exactly analogous to what we were discussing yesterday, that if you make the continuum, if you make the integral assumption of this sum, you will get that the sum is 0. But if you do the sum actually, then you will find that it's small but not 0. This was interpreted as one version, if you wish, of information problem. It's due to Maldacena.
So you expect something, but you get something else. So here, whatever we have done is not seeing unitarity. So we will lose things. Now, how do we resolve? Now, this is, I'll just mention this.
Just like
Yes.
when we show that at large time with analysis, this 2-point function.
Yes.
So one can expect that this OL QFT theta so it gives us the expectation level and we don't have to further think down.
This is 0. That's what it means.
That's 0. So means once the conclusion means QFT theta.
No, nothing about TFT tilde. What I was saying is that last time, if you remember, we were trying to argue that I did it with spectral form factor, but you can do it with 2-point functions also. That if you are able to compute this 2-point function and able to compute it for all times, you will see at very large times, especially at times which is much bigger than the inverse temperature, you will see that the object may be small but cannot go to 0. But here I see a smooth function which is smoothly going to 0. That's the problem, and that mismatch is the lack of knowledge, because I'm using a certain geometry to describe my CFT. And that geometry and that calculation is not able to see all the information that I should see to get unitarity. Okay? So how do you go solving it, or how do you resolve it? One possibility is that there exist new/novel solutions to less clear but find a clever way. That's all I really know. Now, the first one is very hard. It's much easier to say, but you have to go and find solutions of Einstein equation which are not a black hole, but shares a lot of properties with a black hole. It looks like a black hole. It's not easy, but has been done. The other thing is completely, not even well defined. It's well, if you can do it, you can do it. I have nothing to say. I don't know how else to say this. But, and that has also been done. The other more familiar method, perhaps, because it might be more familiar, let me just mention it. More familiar. So I'm going to conclude the same statement, but with a slightly more familiar calculation. What are we used to do? So for example, given a black hole or given any geometry, let's say we study some scalar field in it, right? So we have some equation box or box square phi equal to 0 or some mass, etc. And then we solve it, find this is exactly, suppose this is exactly solvable, we use boundary conditions, and when we use boundary conditions, we use ingoing boundary conditions at the horizon, right? Use ingoing boundary condition at horizon. And if you do that, so this I can now quantize, right? I have the full solution, I have all modes, I can do my usual canonical quantization. So the spectrum, instead of a normal mode, gives you quasi-normal modes. Which means that the frequencies are complex, they have imaginary power, and if with this you compute the partition function, you will see because the quasi-normal modes had an imaginary part, your partition function will always be decaying. So something like that. Again. Yes. And that's obvious here because I put that things only go inside the horizon, nothing comes out. So how can I retain unitarity? Yes.
So this one thing we can try to so if I do a classical gear situation, then I expect this to be 0, right? This
Sure.
OL over.
Sure.
And your CFT calculation is giving this to be 0 at time.
CFT calculation, if I am able to do it, it will not give me exactly 0. This is the gravity calculation. This is the gravity calculation. CFT calculation will not give me, in fact, I don't have to go to CFT. Any standard quantum mechanical will not show you this. So it's really very counterintuitive that way. So this means a similar decay. And therefore, we again run into problems. This might be a bit more familiar to you with the wake of all these ring down modes and so on and so forth. Those are the quasi-normal modes. So, but that cannot be the whole story. I mean, unless you want to lose unitarity. So, one point is the following, that if I see several options appear at this point. One is that, well, this starting point is problematic. That can be one option. One option could be, okay, I'm really doing some ingoing boundary condition at the horizon. How can I be expected to retain unitarity? So, I must use some different boundary condition. This is not right. In other words, the horizon must have a structure of some kind. So, how else would it get reflected? I mean, naturally it would just fall in. If it has to do something else, then there must be structure at the horizon. If you assume that, then that ties slightly well with this strategy, where people actually try to find out solutions of much more complicated systems, supergravity and so on, motivated by string theory, where you have really structure at the horizon scale. So, you really hit something, you don't go in. So, you hit something, you come back, that will avoid the decay problem and you get unitarity by definition. But this is a very difficult problem to solve technically, extremely complicated. So, so this is the basic of TFT, and I wanted to show you something, but instead I think in view of time, let me fast forward a little bit and show you something else. So, that will and everything else that I am going to show you is also, are also completely dependent in some sense in terms of these pictures. So, it should not be too difficult, but let us see. All right. So, now what we want to do is, I hope it is at least morally clear that if we want to understand these statements or we want to understand these black holes, we have to keep computing correlation functions of various kinds. In particular, more precisely, more fancily said perhaps, is that we have to understand the entanglement structure of stuff, of a black hole geometry. But I am not going to really discuss a lot about entanglement, anything about entanglement really, which I think is almost almost an accomplishment, because I don't know whether I would be able to give 3 talks in ADSCFT and not talk about entanglement 5 years back, but now there are some interesting calculations, I can completely bypass it. So, but talk about correlators, really garden variety correlation functions. So, let me now slightly switch gear and talk about shock waves. It will become in a moment clear why this is important, mostly following works by Susskind, Stanford, and others of course. And if you really want to know a bit more about this subject, I highly recommend any lecture that Stanford gives. It's really amazing. So, let me start with the BTZ geometry, which is, it's called the BTZ geometry, which is D equal to 2. So, the black hole metric ds square, let me just write it down, r square minus r square dt square minus plus dr square by r square minus r square d phi square. As you can see, phi is an angle, it's a 3-dimensional. Fine, and let me give you some things. This r square is, well, let me just write this down, 8 g Newton m. Beta is 2 pi by r. Yes, that's it. In the Kruskal coordinate, well, yeah, okay, let me write it down. So, let me first draw this square and I will ignore the singularity for a good reason, because in 3 dimension you do not actually have a singularity here. If you wish, you can still have these wiggly lines. So, these are the 2 horizons. All right. So, the boundaries, so let me write this down, write down the metric of this space time in the so called Kruskal coordinate, and I will copy it. So, this is minus 4 du dv plus 1 minus uv, yes, uv square d phi square 1 plus uv square. So, there are 2 boundaries, this is uv is equal to minus 1, this is uv is equal to plus 1, and maybe this is u equal to 0, this is v equal to 0. These are the 2 horizons. This is the structure of the eternal black hole. Okay? This is eternal. Nothing is changing. All right. Now, so as we learned that geodesic distances etc. can be very easily computed in this geometry, just because I know the geometry and I can do those calculations. Now, consider the following, that I throw in particles, by that I really mean energies, could be, without specifying what it is, from, let us say, right at Tw, which is where Tw is a very large negative number, if you wish, which means that in the far past you threw away something into the black hole. So, it should increase the black hole, that is the standard intuition, with energy E. So, this has energy E. So, then at t equal to 0, the energy perceived would have a shift, which is E over R e to the R Tw. In other words, if you take Tw to be very large, this energy will be extremely large, right? That is the usual gravitational red shift or blue shift, anyway, shift. So, what that means is 2 things. One is that there will be a high back reaction. Two is that these particles will follow null paths. Because they are highly energetic, so I can just approximate them as null particles. Now, my problem has simplified, because all I have to do is to somehow calculate, if I threw in null particles very far past, how does this geometry change, right? And the calculation can be done without getting into, without really solving Einstein's equations, but what you can do is you can imagine patchwise solving it, because you see the back reaction will become extremely large very near the horizon. If you stay far away, then it's just a small particle going in. So, if you are very far away, this picture remains same on both sides. It's only near the horizon, when the particle comes near the horizon, it becomes extremely highly energetic and things happen. So, that can be done with a gluing procedure, where you glue 2 of these squares onto each other with some conditions. Okay? So, one square has certain parameters like r, for example, m, etc. The other square will have a different parameters, let us call it r prime, m prime and so on, and now I need a gluing condition. So, that gluing condition, if you satisfy, so this can, I will never learn this. Gluing can be done, and if you do the gluing, let me just give you the picture. Hopefully, I'll be okay. Not do too bad of a job, but let's see. Gone back to the singularity, but anyway. So, this is the object that is being thrown, if you wish, and let me draw two perpendiculars, one from here and one from here, where they do not meet in the middle. So, you see I had a square. Now, because of this, because I threw in this null dust, that square became a parallelogram. What is that? Yeah, rhombus, right, with a mismatch in the middle. So, a gap, if you wish. And it turns out that is really all. If you do this correctly, this captures the back reacted geometry.
So, because the sketches we were doing, one is for when the particle is near the horizon, and the other one is when it's far away. Is that true, or?
No, I mean, so what will happen is that because you threw in the particle, there will be really a gap between these two lines. That's all. So as you can see that the picture is tilted globally. It's not tilted locally.
All that the back reaction does is to create this gap.
Is to create this gap. That's it. That's it. And now it so happens that, I mean, once you solve, this is a solution of the gluing condition.
From equations to understand this gap is if you have to do stress tensor of this lambda, there is a delta function
Yeah.
near the horizon and the metric has a theta function. So you take derivative of the theta function, you get delta function.
Yes.
That is why you have to.
Good. Yes, indeed. Yeah. Good, good. So, all right. So 10 minutes. So let me not get into the details of some of the things, but give you one answer, something that we have already seen. So, all right. So now, since I have a geometry, now I can again compute my correlators, because that's what we have learned. So suppose, I want to compute the following thing, that I have a phi left, phi right, but how should I denote this? Well, in the back reacted geometry. Okay? Suppose this is what I want to compute, and let me define it. It's a definition because I just want to normalize it in some way. So this is some W plus phi L, phi R, W acting on this thermophile double state, normalized by this W plus, W dagger, sorry, this, right. So W, if you wish, is the particle that I threw in, which back reacted and created this non-trivial state, and in that state I want to compute phi left, phi R. Phi left, phi R are two probe fields, like the ones that we just did before. So, all right. So now, as we have learned that if I want to compute this, what do I have to do? I have to analyze geodesics in geometry. In the geometry, right? And it turns out, because it's not very different from the original one is really very standard. This one is also not so bad. I can actually analytically do it. I can compute my geodesics analytically in such a geometry, and this geodesic distance calculation gives me that phi left, phi right, back, if you wish, is something like this, 1 over 1 plus, well, things I didn't introduce, but let me be, yeah, okay, I can write it. Yeah, 1 over g Newton e to the r t w square raised to some power 2m maybe, or 2 small m should be, really, anyway. small m phi. Okay, it's an algebraic expression, which if I look at it, I can, my first instinct should be to expand this, right, because G Newton is very large, so this is a small number, and this is m phi is the mass of the scalar field. So this correlation function was really found out. Yeah, so let's just say that this scalar field has a mass m phi, and that's where it enters. Okay, roughly speaking, this is the expression where R is the mass parameter of the metric, TW is the insertion time, if you remember. G Newton is a large Newton's constant, that's all. Now, because it is large, our natural instinct to say that this is less than 1, so therefore, let's expand it. So, if we do that, what do we get? We get 1 minus some 2 m phi over G Newton e to the R T W, right? Now, so this is equal to this correlator. This look very similar or familiar to you, because we discussed last time that OTOCs in a system which is chaotic perhaps, or at least growing, has an exactly same behavior. So this is an OTOC behavior where you see that normally, so in going from this line to this line, our assumption was that 2 m phi over G Newton times e to the t R W is less than 1, and that, if I write it down, so this is log of, sorry, yeah, okay, log of E T R W is less than log of 2 m phi over G Newton, sorry, the other way, excuse me. Anyway, so this will give you that this time is less than T W, not R W, 1 over R log of n, once you identify that 1 over G Newton square is basically n square. Okay. So, what I want to say from here is that, well, of course, this is not an OTOC calculation from the bulk, because all we are doing is a 2-point function calculation in a perturbed geometry, right? So, what is OTOC here? So, that has to be interpreted, etc. But, and I mean not interpreted, in order to do OTOC calculation, you have to do a little bit more, but at the end of the day, you will be ending up calculating exactly the same thing. And the point is that the OTOC behavior that was advertised for thermal states, that it has a growing behavior versus, I mean exponentially growing behavior with time and so on and so forth, is what is visible here. And moreover, it allows you to define a time scale beyond which this behavior is no longer true, beyond which it becomes this, right? That's exactly the OTOC expectation also. So, therefore, from the bulk, if you wish, we have managed to reproduce the expression of what we expect of an OTOC. You have to do a little bit more to be very precise, but probably that's not, yeah, that's certainly not advisable now. But essentially this is the story. So, now as you sorry as you can see, this is a statement about a correlation function. So is this one. It is also a statement about a correlation function at the end of the day. And what we managed to show is that these correlations, which are also highly non-trivial, they match, of course, to the expectation, and also and so on and so forth. And just as a sort of a concluding statement is that some of these correlations are really what underlies a definition of, let us say, how information spread in a quantum system, and so on and so forth. So, in that sense, what we can see here is a way how quantum information spreads in the CFT to be reproduced in a gravity calculation.
One question. Suppose I take this TW to be really, really large.
Mhm.
Then I'm going to get this exponential decay.
Yes, yes, yes.
That still doesn't match with
No, that matches. So, for example,
this exponential is something that doesn't match with the safety.
no, if you do the identity block large C CFT calculation, this is exactly the expression. So, in large C CFT, you exactly get this, and then you do the expansion and get that.
No, that I understand.
Yeah.
But
So, at large times, it is decaying.
see, you made a statement that this exponential minus a divided by meter,
Mm-hmm.
behavior of this phi and phi r.
Oh, I see what you mean. Okay. So, okay, good.
So you can
But,
interpret this TW as the time taken for the process, because that's the time taken by the particle.
right.
I still think that this correlation function will go to 0 at long times.
No, but it does go to 0 at long times. I mean, exponentially, yes. Sure. Let me see what I want to say. I think, good. One thing I'm tempted to say right at this point is that we have already accepted that such things are going to be true in my gravity calculation, unless I want to include really very quantumness some way, which is not done here. So, no matter what I do, I will still get answers of this kind. Yes, I think so. So, even you rightly pointed out, even if I compute very high point function, 4-point function, I still see this exponential decay to 0, which it should not happen, which it should not do. And indeed, I think there are calculations where in the geometry, instead of taking a black hole, you can sort of try and mimic a microstate in 3 dimensions, basically because you have CFT to power, and you take heavy enough states in the CFT calculation and show that you get the answer that you get from gravity, but then there are other terms which start coming in once you go to very long times. Yes, but that can be done in 3. Somehow that quantumness has to come, indeed, and that I think in CFT 2 has been done by Kaplan and. Yeah, that is true. So there are corrections, of course. There are corrections. This is not an exact answer, which will reduce. But I think the really neat calculation from a CFT is in CFT 2. Yes, indeed. So I think that's a good place to stop. It's exactly 5 o'clock.
There we saw that at tends to infinite, means in the TFT it is 2.26 hours. So when at infinite time is when time is large, it should be reduced to 0.
Yes.
But it is not the fact from the CFT.
Yes.
So it somehow resolves my problems when we are talking this back engagement. So how can you show that
No, it's, well, if you take very large, if TW is very large, this is the only term in the denominator, right? And so that will go to 0. You have an expression where the denominator becomes extremely large, so it will be 0. It will smoothly go to 0 like this one. So as he was pointing out, there is, even this function doesn't see any resolution. Because you see, we are starting with a smooth geometry. The fact that I can have a smooth geometry tells me perhaps that this will always happen. That's why people like this. But the problem is it's hard. It's really hard, yes. Yes. No, so what you can do, you can start with a heavy state and then do this 4-point function calculation. In the heavy state, yes, indeed, at you can make you can expand the answer in 1 over C. So the leading order answer will be this, but once the 1 over C corrections come in, yeah, yes, you are right, you are right.
Okay, any other questions? If not, let's thank Warren for a very nice talk.
Thank you. You should get that.
So, yes, so I'll be talking about chaos in driven conformal field theories. So this is based on a recent work which has been done along with Shuchetanda, Bobby sir, Anubda, and Shomnath and Krishnendra Sengupta. I'll be talking about a special class of correlators called out-of-time order correlators, which has been known to provide a diagnostic for early time chaos in a typical non-integrable quantum system. So, basically I'll ask this question that how does this out-of-time order correlators behave in a particular non-equilibrium setup called driven conformal field theories, in which the Hamiltonian of the system has been subjected to either continuous or discrete periodic drive protocol. So I'll come to this, what I mean by continuous or discrete periodic drive protocol. So in the morning we have heard lectures about the drive protocols, and also now we heard, and also in the other days we have lectures about out of time order correlators in great detail. Okay, so this is a brief outline of my talk. So I'll be talking about driven conformal field theories. At first I'll describe what do I mean by driven conformal field theories. Then I'll talk about the general OTOC computation in little detail. And then I'll be talking about OTOCs and our setup in driven CFTs. And then I'll come to our main results, and finally I'll conclude with some remarks. So what do I mean by driven conformal field theory is that, basically I'll be talking about periodically driven conformal field theories. So it simply means to evolve the system with varying Hamiltonian within a stroboscopic time period t, and repeat this process for integer such time period, so that the total time is given by n times capital T. So such a drive protocol can be used to evolve the system in a way that the within each time period t, this Hamiltonian is updated continuously or in discrete state. Also, yes, as I've already stated, that will restrict ourselves to periodically driven CFTs, and also to the discrete drive case for the rest of the talk. The driven Hamiltonian is given by it's specified by this deformed Hamiltonian, where we deform it by some functions fx and gx, and with the help of these functions we tune the chiral and antichiral part of the energy momentum tensor, and so these we control externally to drive the CFTs in different ways. Meaning that, for example, if I consider a discrete drive, and within the time period t, I subdivide the time period and intervals t1, t2, tk intervals, and during each interval tj, the Hamiltonian that I update the Hamiltonian by changing fx and gx. For simplicity, we'll take fx equals to gx for our computation, and also we'll choose fx in such a way that the Hamiltonian is built out of the generators of the SL2R algebra. So the main advantage is that such drive will lead to time evolution operator, which has this SL2R generators, and this generates the Mobius transformation in the complex plane, where the net effect of the full evolution is given by the C1 times the product of this such SL2R matrices. So in Heisenberg pictures, then this time evolution of a primary operator is nothing but the dynamics of operative evolution under conformal transformation. So what really is so it's a conformal transformation where this Z is getting Mobius transform to Zn, and this time small t is nothing but n times capital T, and this u's are products of all the u's at time t. So, so I'll before going in detail, I'll talk about a minimal setup. So, suppose we consider a discrete drive, a two-step discrete drive. So, for time interval t1, the Hamiltonian is h1, and for time interval t2, the Hamiltonian is h2, and then we repeat this for n times, and this is what I mean by discrete driven CFT protocol. So, this discrete drive, and for our case, we have considered an explicit Hamiltonian like this. So this is it's better known as a deformed SSD Hamiltonian or sine square deformed Hamiltonian, and this H1 is when phi is equals to 0, and H2 is phi is not equals to 0, and now we can write this M's this matrices, this, and this alpha beta is now given by this can compute it, and for nth evolution we multiply this m0 and m1 for n times. So such driven system can be classified in different dynamics or phases, heating phases, non-heating phases, and there is also a phase boundary by tuning these drive parameters. So here the drive parameters are phi, T1 and T2. So by we can see three different phases, and the condition is given by this, that when the multiplication of M1 and M2 and this trace of this multiplication of this matrices is mod of trace of this this multiplications is greater than 2 is called heating phase, is less than 2 is called non-heating phase, and if it's equals to 2 then is the phase transition. Okay, so I'll be briefly describing the general OTOC prescription. So we start with a normalized 4-point Euclidean correlators of this form, where we take two primary operators and all in different Euclidean coordinates. So the two operators have conformal weights. Two are W, so having conformal age W, and other two are V, having weights age V, and so it's well known that these can be written as functions of cross ratios. This has also been discussed by Deepta Arkoda, and this is a function of. So this depends on the dynamics of the corresponding CFT, and now using I epsilon prescription, this tau I is analytically continued to Lorentzian time plus I epsilon, and then epsilon limit is taken to 0, and different time orders Lorentzian correlators are obtained depending on the order in which epsilon is taken to 0. So for this particular ordering, when the epsilon 1 is greater than epsilon 3 and is greater than epsilon 3 is greater than epsilon 2 and 2 is greater than 4, and then it's taken to 0, the corresponding Lorentzian correlation function will give me OTOC. So for 2D CFT on the plane, the function f eta has branch cut along the real line, that is from eta equals to 1 to infinity, and the time ordering or the out of time ordering depends crucially on the path taken by eta during analytic continuation. For OTOC in the thermal state, in a 2D CFT, either eta or eta bar must cross this branch cut. This has been shown, stated in the papers by Robust and Sanford. And in the large CFTs, when HW by C is held small and HV is large, the dynamical function is exactly known, and these OTOCs are known to show exponential behavior, and therefore providing a signature of chaos. So we follow the general prescription and we set up our calculation and calculate the OTOC. So we consider the Euclidean correlator. Here we consider this two W's sitting at initial location x1 and V's sitting at initial location x2 on the cylinder at tau equals to 0, and then we map the cylinder to the plane, and we keep the V's fixed in time, and we evolved W's with the Fourier's transformation in stroboscopic time, and then we do the analytic continuation in I epsilon prescription. And the interesting thing that we find here is that there are two points called special points called fixed points, which plays a very crucial role in this like OTOC calculations. So what is a key difference from undriven CFT is that the analytically continued curve eta crosses the real axis at finite value in eta complex plane if and only if this condition, that is Z1 n is equals to Z3, and this is satisfied, and this in turn will lead to a allowed domain in the initial operator location, which is bounded by the fixed point. The fixed points are those which doesn't evolve with time, and for eta greater than 1, we see that eta will be greater than 1 for the OTOC configuration, which is epsilon 1 greater than epsilon 3, greater than epsilon 2, and greater than epsilon 4, and eta is less than 1 for TOC case. Okay, so we come to the main result. We find that in the heating phase of the large CCFTs, the OTOC shows an exponential behavior, but only for a particular range of x. The condition for which either eta or eta bar crosses the branch cut is given by a condition like this, and if the initial locations x1 and x2 are within the fixed point, if two are in same side of the fixed points, then only this eta will cross this 1 while during the analytic continuation, and if it's on the other side, either side, like two are the initial locations are on the other side, like either side of this fixed point, then eta will never cross 1. And this is a plot showing the same thing, and this green region basically indicates the allowed region for eta, and the gray region indicates that for the eta bar. And in the late time limit, the cross ratio will behave like this, where we can see an exponentially decaying factor in the this e to the power minus 4 n phi, which is exponentially decaying in time. And now if we substitute this eta, since this f eta is kind of known in the large C cases, so if we substitute this eta in f eta, and now we calculate, we get butterfly velocity and this Lyapunov exponent. This Lyapunov exponent is, as we can see, these are this is dependent on the drive parameters phi, t1 and t2, and this butterfly velocity is position dependent. So some comments are there that the position dependence of the butterfly velocity is a consequence of the lack of translational invariance in this system. So in the non-heating phase, there is no exponential growth for any value of x. For the and this is also true if we calculate anything for the, so this is a large CCFT case. If we do the calculation in Ising model, we can show that there is no exponential growth in any of the phases, heating, non-heating, or phase transition. For the continuous drive case, nothing changes qualitatively. We again get a similar range of x for the cross ratios and a position dependent butterfly velocity and scrambling time. And in this case, the Lyapunov exponent is also a function of the drive parameters, and the butterfly velocity can also be tuned using the drive frequency. Also, okay, so now I'll talk about the recent progress and some future directions. So as a consistency check, would always like to compute the 2-point functions and 4-point functions and the entangled entropy from the bulk side and match it with the boundary result. And in our recent work, we have been able to find out the bulk matrix for the different phases corresponding to the SL2R driven CFTs described on the cylinder on the boundary, in the boundary side. And Somnath will talk about in detail about these. And also we expect that in the SL2R driven CFTs defined on the boundary, defined on a strip will correspond to a similar ADS geometry, but along with the end of the wall brain inserted in the bulk. So the bulk geometries that we find are ADS, but with some patches, for the different phases, with some ADS2 patches for some different phases. This Somnath will tell you all about this in great detail. And for the CFTs which are defined, if the CFTs if there are open boundary condition on the CFT side, then it will be expected to correspond to similar ADS geometries, but along with the end of the wall brain inserted in the bulk. Also, we are trying to generalize these calculations for SL2R cases, where things will get trickier since the state of the system changes in every state of the drive, and we expect to see more exotic geometries for these cases. So, thank you.
I see what is the difference between heating and non-heating?
Yeah, so we check the calculations for Ising model in heating phase, I think. So there you won't be able to see the exponential behavior. I think no, we have only checked the heating case, since the heating will only was supposed to show you the exponential behavior. Yes.
What is the argument in the scrambling time? Is it telling about something?
Yeah, so when you write the expression, you can write that the scrambling time that the people has already mentioned. So what do you want to know? So the scrambling time was also, yes, so see, yes. So the scrambling time will also be like position dependent in this case, because since these are like breaking the translation in invariance. Yes.
The form of your state that you are seeing its evolution as non-intuitive.
Yes, I have not written down the form. So you can this cross ratio. So there is a form like Fn is known. So if you see the paper by Robert and Stanford, so they have an explicit form that is given. That is more like the form that has been already described there. So there will be a 1 by eta term. So there you plug in eta and you will get this. Since there is already a e to the power minus 4 in t dependence, like time dependence, so you will get that.
Here you are giving some periodic perturbations and seeing how it's changed.
Here?
Here you are giving some periodic perturbations.
Yes, so you one thing you can tell that the state is not changing here, since we are taking only the SL2R. We are, as Diptarko has already told, that this ln which acting on the ground state for n greater than equals to -1 will always give you 0. So in this case, the state is not changing. In really, state is not changing, but still we are seeing this chaos in OTOC, but because there is the time dependence in between, like operators are evolving. If you consider from operator perspective, so operator is evolving, and this OTOC can see this chaotic behavior.
So why was this happening around place of some operator?
So so you can tell that in this type of system there is compute a like a Casimir of a quadratic Casimir, and then you can distinguish like 3 different phases. And also from a physical point of view, I can tell you that when Wen and the collaborators, they have seen that when you take a cell Q2R algebra, so there you get like entanglement entropy, like in these 3 phases, the entanglement entropy dependence on time is different. Like for the heating phase, entanglement entropy will linearly grow, and for the phase transition, it will be logarithmic, and for the non-heating, it will be oscillatory. Yeah. So depending on this phases, like if you differentiate these phases, in one phases you will see this, and the other phase you will see. Yes, you can ask me like later, maybe.
Yeah. So welcome everyone. So I'll start from where Vaishali left off. So I'll be discussing the bulk dual of the driven safety that she has discussed in detail. So this talk is based on this paper, which is done in collaboration with Arnav sir, Vaishali, Bobby sir, Krishnendu sir, and Suchadanda. So this is the brief outline of my talk. So at first I'll spend few lines on the boundary setup that Vaishali has discussed already in detail. So then I'll go to the general strategy for finding the bulk dual of a particular CFT state using ADS CFT. Then for our example, what are the matrices that we get in different phases of the driven CFT, and then I'll discuss about how to understand this phase transition from the bulk perspective itself, and then I'll finish with some future directions. So this is the boundary setup. So in this talk, we'll mainly focus on simple two-state discrete die protocol. So by that what I mean, so we start with the ground state of the 2D CFT on a circle. Then we evolve the system with Hamiltonian H0 for time t0 and with H1 for time t1. So and we repeat this cycle for n time. So basically by that what I mean is that I start with the ground state that is written as 0, and we do this step and we get the state size. So what we will try to answer is that what is the bulk dual of the state psi basically. So this thing can be written in this form. So basically this H effective, that is the effective Hamiltonian or the stroboscopic Hamiltonian that Krishnendu sir was talking about, this captures the dynamics of that whole transformation. And for our case, like we consider that H0 is the undeformed CFT Hamiltonian and H1 is the deformed CFT Hamiltonian. To be specific, they are of this form like T00 dx. This is the usual CFT Hamiltonian. Then we deform that with some function 1 minus tan hyperbolic 2 pi times cos 2 pi L. So yeah. So in this case, we can find the effective Hamiltonian, and that is of the following form. And it consists of only the global part of the conformal generators, and this alpha, beta, gamma, they are basically dependent of the parameters of the drive, that is T1, T2, which were the time periods for which we are driving with Hamiltonian H1 and Hamiltonian H2, and phi is the parameter that was present here in the Hamiltonian, if you see in the last line in the H1. Now, such kind of evolution leads to 3 qualitatively different dynamics, and based on the sign of the Casimir of the conformal transformation that is generated by H effective. So where is this conformal thing coming from? Because if you see that effective Hamiltonian, it's made out of only the global part of the conformal generator. So the time translation that this Hamiltonian will generate, we can think it as some conformal transformation in the complex plane. And based on the sign of the Casimir, we distinguish 3 phases. So when this combination alpha square minus 4 beta gamma is less than 0, we call it heating phase. When it is greater than 0, it is known to be non-heating phase, and for equals to 0, it's just the phase boundary. And now the question that we want to answer is that what kind of geometries do these phases correspond to in the bulk? So first I will discuss like how to get the geometry of a particular state of a CFT. From ADS CFT we know that in the semi-classical limit, the states in CFT are described as geometries in the gravity theory. For example, the vacuum of a CFT we know to be the dual of some pure ADS geometry plus some quantum fluctuations. And the geometric dual can be found by solving Einstein equation with negative cosmological constant, where the source term, the right hand side of the Einstein equation, is given by the expectation value of the boundary stress tensor that we calculate in that particular state, whose dual we are trying to calculate. So this is for the equilibrium case. And now, so we like when the state is changing, the state is evolving. Now we have to know like how to get this transformation from in the bulk, how to understand that time evolution in the bulk. So, yeah, bulk dual means you have already heard about ADS CFT correspondence. So by that what I mean is that in the CFT, if there is one state, you can describe the same thing as some geometry in the ADS side. So that ADS geometry I am calling as bulk. The boundary is the CFT state and the bulk is the geometry that we are talking about. Sorry? Yeah, dual means these two theories are same. So the main statement of the ADS CFT is that like the quantum gravity in ADS, you know, that is to be the dual of the CFT in one dimension lower. So by dual I mean that thing only.
So in this theory, when you are evolving with the Hamiltonian H0 and H1, both are assumed to be time independent. That's why exponential.
Both are time independent, but the effective thing that you are getting, that is time dependent dynamics. As you can see, because you are changing the Hamiltonian with time. Like for time t0, I am evolving with h0, and then for time t1, I am evolving with h1. So yeah. So to find this thing, there are two steps. So first step is that we will have to find the bulk dual of the boundary transformation that is generated by the Hamiltonian. For example, if the Hamiltonian generates conformal transformation, which is in our case the situation, and then we know for ADS3 CFT2 case the bulk diffeomorphism corresponding to any conformal transformation, and hence we know the metric in the particular gauge. So like if we are talking about any general conformal transformation, this is the whole story. But if we want to make it sure that in this case, what is the difference is that we are changing the state with Hamiltonian. So we have to make sure that the parameter of the transformation is time. So then we need the second step, that is to make the parameter of the transformation as time. We will have to go to co-moving frame along the curve that is generated by the Hamiltonian. Yeah. Now in this setup that we are considering, as I have already discussed, the effective Hamiltonian is made out of these global generators H0, L1 and L-1. So in that case, the CFT state, we have started from the vacuum of the CFT, so that state will not change because we are changing with the global generators. So we will have to worry only about the step 2. So we will have to make this parameter of the transformation as time. So for that, what we do, we just leave the boundary effective Hamiltonian into the bulk by replacing the global Viracharo generators by its ADS3 representation. So you can see that L0, L1 and L-1, I have replaced it with some bulk representation of these generators from the like ADS3 representation. And then we want to rewrite the ADS Poincare metric in terms of the tangent curve that is generated by this Hamiltonian. So interestingly, what we found is that the different phases of this drive correspond to ADS3 matrices only, but foliated by some different bulk ADS2 slices for different phases. For example, in the non-heating phase, we get a metric like this. So if you consider the phi equals to constant slice, that is the metric of a just global ADS2 patch. So pictorially, so here this theta and t, these are boundary coordinates, and phi is the bulk coordinate. So pictorially saying, so this is the ADS2 patch, that this, if you think that some observer is moving along the curve that is generated in this non-heating phase, so that can cover whole of this space. This is the picture of a ADS2 slice, like I am drawing it like this. And for the heating phase, you can see here in the previous case it was just sine hyperbolic square, but it gets changed to sine hyperbolic square, and this patch, this constant phi patch, that is now the ADS2 black hole patch. And in this case, pictorially, an observer can only see up to this part of the geometry, not the whole geometry. And on the transition line, the constant phi slice is just the ADS2 Poincare patch, and in that case, the observer can see up to this point of the geometry. Like it can cover only this part that is bounded by these red lines. And so here are some comments. Now the presence of the horizon in the heating phase, because we saw that there was some black hole metric in the ADS2 patch. So this presence of the horizon is the reminiscent of the fact that like in the bulk dual picture corresponding to undriven thermal CFT. So hence we will expect that there will be some chaotic behavior from the bulk OTOC calculation as well. And for this, like to check whether the calculation was right or not, so we calculated few things from the bulk side and we tried to match that with our boundary calculation. So for that, what we do, like we have calculated some 2-point functions of the scalar field in the geometries that we have found out, and we have calculated, we have matched those answers with our boundary calculations, and we have seen that those answers are matching. And also we have calculated, like set up the shockwave calculation in this bulk matrix that we have got, and we have calculated the Lyapunov exponent from them, and we have matched those calculations with the bulk, our boundary results. Yeah. Now to understand the phase transition from the bulk, what we do, there are two ways to do. So one is the when we are considering only a probe bin, that is we are saying that we are inserting one brane in the boundary. By brane I mean some two-dimensional hypersurface, but that is no back reaction. That is known as probe brane. So for that case, we take the action of the brane to be of this form. This S and theta are the coordinates that are appearing in the metric, and so I have considered this kind of. So here gamma is the induced matrix. So I have considered this kind of function. I have taken the phi to be some function of theta. So in this case, we can solve the brane profile, and we found out that some phi equals to pi by 2 is one of the solution of the brane profile in all the phases. And if we sorry, wrong. Oh, sorry. Oh yeah, here I have changed it. I have changed it in the last moment. Sorry, yeah. So yeah, and we have seen that we have calculated the on-cell action on these branes while transitioning from one phase to another phase, like from heating phase to non-heating phase, and we found that like there was one jump in the on-cell action, which is one signal of a phase transition. So we can understand the phase transition from the bulk in this way by inserting some branes, and also we have done the same calculation by inserting some fully dynamic. Sorry, these two, just ignore these two spellings. So I've somehow messed it up. So yeah, so we have done the same calculation by inserting fully dynamic branes, and in that case also we could see this kind of phase transition from the bulk itself. So as a future direction, like as Vaishali has already like talked about it a little bit, like so in an ongoing project we are trying to find out the bulk dual of a more general drive, that is SLQ to a drive. So in that case the generators are made out of L0, LQ and L minus Q. So unlike the Q equals to 1 case, in that case the ground state will change under time evolution with this kind of Hamiltonian, like if I consider L0, LQ and L minus Q. So from the bulk perspective, this means that the geometry will be time dependent. So it will be interesting if we can work that out, and also it will be interesting if we can study these drives in the presence of boundaries in the CFT. So it is known that the boundary, like in the presence of a boundary in the CFT means some presence of some end of the wall brane in the bulk. So it will be nice if we can understand how these kind of drives change the, like affects the brane profile and also the overall geometry in that case. And also, yeah, just it will be also interesting if we can set up the OTOC calculation in presence of the brane, and we can match the answer with some boundary calculation. Yeah. So thank you.
So where did A enter into your brain?
Sorry.
The time.
Yeah. So on here. In the tension, yeah. Like in the, I have forgotten the exact dependence, but it was something like tan hyperbolic or something, I think. And yeah. Yeah, like we have actually done this calculation for the transition from heating phase to non-heating phase only, and we have seen that there is one jump in the on-cell action. Oh, Yeah, that is the correct spelling actually. The brain mean that you are you are considering one hypersurface, like the geometry that we got, if you see, I can go to the metric. So it is some three-dimensional geometry, right? So we are considering, we are taking one profile of the phi, we are taking, I have written here also. So we are taking some phi as some function of theta. So then if you put that back in the metric, you will get some two-dimensional metric, right? So you can think that there is some two-dimensional hypersurface on like in your geometry, and that is what we are calling as brain.